Chairperson, Mr. Wandumaganya Adis, Head, the Academic Program Director, Tepi Campus, Mizan-Tepi University. Now I request Mr. Wandumaganya Adis to address the gathering as well to invite our today's keynote speaker. Welcome, sir.
Okay, thank you. Am I audible now? Shall I continue?
Yes, you are audible. You can continue.
Okay, thank you. Respected directors, deans, coordinators, and heads of departments on all academic staff of Mizan-Tepi University, as well as participants from different national and international universities, as well, and speakers and presenters across the globe. And on behalf of Mizan-Tepi University Tepi Campus academic community, it's my great pleasure to welcome all of you to the second day of this international virtual conference on research in mathematics, which is the first of its kind here in Mizan-Tepi University. So, as one of the three campuses of our university, Tepi campus is carrying out its singular learning, research and community service activities with colleagues and one skill across 16 departments here in Tepi campus. So we are more than delighted to host this first international conference of Mizan-Tepi University here in Tepi campus. So accordingly, I would like to congratulate Department of Mathematics and College of Natural and Computational Science for this wonderful breakthrough achievement. I would like also to extend my heartfelt thanks to all the organizing committee members, plus all the officers' successful contribution of this event. So on top of that, I would like also to urge other departments and colleges of Mizan-Tepi University and our campus to take this conference as an experience or a stepping stone to play their part. And I hope we will meet soon on this stage again with other departments or disciplines and platforms. So, like the first day of the conference, I think or I hope I will have an open, constructive, and fruitful discussion. So once again, thank you all for your effort and participation in this conference. Saying all of this, I would like to introduce this session's keynote speaker, Dr. Arvind Massey, who is an assistant professor in Department of Mathematics, Manav Rajna University in India. Dr. Advin has completed his PhD degree from Department of Mathematics in Jamia Millia Islamia under the supervision of Professor Khurshid Haider, and the thesis entitled Geometry of Light-like Manifolds in Semi-Riemannian Manifolds in 2013. He has started his teaching profession in the year 2011 from Department of Mathematics in Jamia Millia Islamia in New Delhi, India. And in July 2013, Dr. Massey joins Satyag Darshan Technical Campus as an assistant professor of mathematics. He also holds a post of examination in charge of the college. And on December 1st, 2014, he joined Department of Mathematics, Manav Rajna University, as an assistant professor. And on top of that, he is an experienced faculty with a total of teaching and research experience of which ranges in like 12 years. Dr. Massey worked on light-like geometry of semi-Riemannian manifolds, which is an extension of manifolds in Riemannian geometry. Light-like geometry plays a vital role as an integral and metric is. And as in general, the metric is not always positive, definite, but in light-like geometry, metric is a semi-definite, so it has many applications in mathematics. His current research includes the study of geometry of light-like semi-manifolds of golden semi-Riemannian manifolds, pointwise light-like semi-manifolds, wrapped product-like semi-manifolds. He has published many research papers in national as well as international journals. And today's presentation topic will be geometry of geometry of quasi-bislant submanifolds. So I would like to invite Dr. Arvind Massey for this stage. Thank you.
Thanks a lot for the introduction, and I'm very thankful to all the organizing committee of this conference, the first international conference on recent researches in mathematics. Now I would like to share my screen, and we will have a healthy discussion on what are the basics. So we will discuss what are the basics research field in differential geometry and what are the scopes of our research in differential geometry, basically when we are talking about quasi bislant submanifolds. Is it my screen is visible, shared with you all?
Not visible, sir. Yeah, sir, visible.
Okay, thank you. So the title of my today's talk is Geometry of Quasi Bislant Submanifolds. And we will discuss what is the geometry of quasi bislant. But before this, I would like to understand what is manifold. Okay, since we know that it consists of slant submanifolds and bislant submanifolds. But before this, we should know what is manifold. So we will have some definitions of certain manifolds which we will use in our research. Okay, so we will discuss what is manifold, and there are certain these are some of the types of manifold: Scalar manifold, Sasakian manifold, Convexo manifold, and cosymplectic manifolds. Later on, we will also discuss what is submanifolds and what are the structures which we are going to study in our research. When we are talking about the research, we have to know what are the basics definitions of CR, semi-slant, what is slant, what is bislant, what is quasi-hemislant, and later on, the main topic of today's talk is quasi-bislant submanifolds. In between, if you have any doubt, if any you have any query, you can ask in between the talk. Okay. So what is basically a manifold? As we know, a manifold is basically a topological space, and where for every point, say this is a point X, and for every point we have a neighborhood which is homeomorphic to Rn. Let me share my writing pad also, so that we can draw some diagrams. With the help of diagram, we are able to visualize the concept of manifold. Let me have no problem. I think it's technical glitch is there. I'm not able to open the. Okay, let's have some example on manifold. So manifold is basically a topological space such that for every point, if there is a point X in that case, for every point we have an open neighborhood, open set, which is homeomorphic to an open set in Rn. And these are certain examples of a manifold. For example, Rn is a manifold itself, and it has dimension n. And we know it. It is known as analytical manifold. And what is atlas in this case? When we are talking about a manifold, atlas is basically a pair, U and phi. What is U? U is basically a neighborhood of any point, and phi is the mapping, homeomorphic mapping of this U. Similarly, we have some other examples of manifold. That is, S1 is another manifold, one-dimensional sphere. That is a torus or a circle. S2 is another example of a two-dimensional manifold. So manifolds are basically of two types, and it will depend upon the dimension of the manifold. So we know that for certain dimensions we have two dimension. Either it is odd dimension or either it will be an even dimension. So when we say that it is even dimension, we came to know that it is an almost complex structure, complex manifold, and we will see what is a Scalar manifold in that case. Okay, so what is Scalar manifold in that case? Scalar is an complex manifold. We know that whenever there is a dimension in complex, it is always exist in pairwise. For example, if I have a root alpha plus iota beta, then its root will also be alpha minus iota beta, as we know that it is always exist pairwise in complex. Similarly, for when we are talking about complex manifold, it is an even dimensional manifold, and when we say that a complex manifold satisfies certain condition, then it becomes a Kähler manifold. So there are certain conditions which has to be satisfied by a complex manifold. Then we say that it will be a Kähler manifold. Then we come to know what is a co-symplectic Sasakian manifold. Let me have, this is Kähler, then we. So what will happen if we have odd dimensional manifold? If there is an odd dimension means base, we have certain bases, and it has linearly dependent and spans the whole sets. Okay, so if it has odd dimension, then that manifold will be a Sasakian manifold, but it has to satisfy certain conditions. Okay, so what are the certain conditions it has to satisfy? So it should have these pairs, that is phi, xi, eta, and g. G is a inner product, and eta xi. Xi is one form, and eta xi is our metric. Basically, G is our metric, and this eta is basically one form, and xi is basically our characteristic vector, and phi is tensor field of type 1, 1. So any structure, this structure is known as contact metric structure. So any manifold together with this structure and satisfy normal condition is called a Sasakian structure, and manifold with Sasakian structure is known as Sasakian manifold. Okay, so these are the conditions when we say that a contact metric manifold metric structure on M is said to be a Sasakian structure if this condition is to satisfy. Okay, so it has, what is phi? Phi is, and again we know that phi is a tensor field. And what are x and y? These are two linear. These are the tangent vectors of M. Okay, so these are the tangent vectors of M. Then again, the next topic for this is Convexo manifold. It is also one of the odd dimensional manifold. So an odd dimensional manifold together with these conditions, that is, it has contact metric structure which satisfy these conditions. These are certain conditions which has to be satisfied by the phi, xi, and eta, so that it becomes a contact metric structure. And for Convexo manifold, we have to satisfy this condition. It was different from Sasakian structure, as you know. Here, del x phi of y, partial derivative. This is the covariant derivative of x with respect to covariant derivative of phi with respect to x. Okay, so this should be equal to g. G is basically inner product of x comma y minus eta x xi. So in this case, this condition is different. That's why it is known as Convexo manifold. Okay, so these conditions should be satisfied by the structures, contact structure. Then if conditions are satisfied by the contact structure, then this manifold together with this structure is known as Convexo manifold. You have to remember these conditions while you are doing some papers, or you are exploring some papers, research papers on manifolds, Convexo manifold. Okay, so this means, it does not mean that we have only these structures. I'm just taking some of the structures which are very known to us, and we are that are very each and every year we are getting some papers on these topics. Okay, so we can say that these are the hot topics in research in differential geometry, basically. So this is another example of a co-symplectic manifold. Okay, so co-symplectic manifold should satisfy these conditions. That is, phi square is equal to minus I. I is the identity mapping, eta x xi. And when phi is applied on xi, it should be 0, and phi is applied on phi, it should be 0, and eta xi is basically the inner product of xi with x. What is x? X is a tangent vector, and that should be 1. Okay, so this is a complex contact structure. And in this case, we have g of phi x phi y is equal to gxy minus eta x eta y. And this is the structure which has to be satisfied while when we expect to the manifold to be a co-symplectic manifold. So this is the definition of co-symplectic manifold. When you explore any research paper regarding co-symplectic, they have to give this definition in each and every paper. Okay. So one of the important topic is you should know what is submanifold when we are exploring and when you are going into research in differential geometry and in manifold theory. The topic is submanifold. You should know what is submanifold. By the name sub and manifold, it is sub means it is a subset of a manifold. And in as a layman, I can say that manifold, let's suppose that there is given a manifold capital M, and there is a subset n of this capital M. We say that n will be a submanifold of M, or M be a submanifold of n. First of all, M should be a subset of n, first condition. Second, there should be embedding. There should be a mapping I, okay, embedding from this M into n. So if any submanifold, a subset satisfy these two conditions, 1 and 2, then we say that subset is basically a manifold, and in some basically we are saying that it is a submanifold. It's again a manifold, but since it is a subset of n, we say that M is a submanifold of n. So there is an example of a submanifold. We know that S1 is basically a circle. X square plus y square is equal to 1 is a one-dimensional submanifold of R2. Okay, so this is a subset of R2. We know that S1 is a subset of R2, and it satisfies all the conditions as we have already discussed in previous slides, that S1 is itself a manifold. Okay, so it is basically a submanifold. Okay. Let me open one of the notebooks so that we can discuss it with the help of Notepad. Let me open the Notepad first of all. Let me open the Notepad. Meanwhile, you can go through this CR submanifold. With the help of diagram, you will definitely understand what I'm trying to say. We should know while we are doing this. Wait for a second. Okay. Meanwhile, it's taking time. Let's have the definition of a CR submanifold. Okay, CR means Cauchy-Riemann submanifolds. When we say that it is a CR submanifold, let me share the screen. Okay, so so when we are talking about CR submanifold, we will talk when we talk about CR submanifolds. So this is our M. Okay, this is our submanifold. Okay, this is our submanifold, and in this we have some. We have tangent space. Let's suppose that this is Tm. Tm means tangent bundle of M, and since we have tangent, so we have a normal bundle also. And suppose that this is T ampere is the normal bundle. Okay, by normal bundle we say that all the collection of all the normal, okay, to this M is collected here, and this is known as normal bundle. Okay, and M together is this one. So when we say that it is a CR submanifold, we say that there will be two distribution. One is D and another is deeper. Okay, so this means, and we have on T ampere also there will be some distribution, and we are talking about Scalar manifold basically here. So we know that when there is a Scalar, it will be J square. J will be the operator, and there is this one. So this is the total distribution of CR. Okay, so this type of manifold is submanifold is known as CR submanifold. So what are the basic characteristic of a CR submanifold? CR submanifolds. So when we say that it is a CR submanifold, there should be two distributions in TM. First is D. What is the characteristic of D? D is basically when we apply J. J is an operator. Okay. So when we apply J, this will not move to anywhere. It will be remain in that space. J will be D itself. That is, it is invariant. It is invariant. It is not moving anywhere. It is invariant. But what is the characteristic of J deeper? When we apply any operators, suppose that we are applying J on this, it will move on to normal. It will be subset of, it will become a subset of Tm per. Tm per. Tm per means it is the part of normal distribution. Okay. So it will become a part of normal distribution. Any doubt regarding CR submanifolds? So CR submanifold, we have two distribution as we can see in the definition itself. So we have two distribution D1 and D2. This one, D and deeper. And the characteristic of D is that if we apply J on D, it will remain in D. And if we apply J on deeper, it will be a subset of normal bundle. Okay. It will be normal bundle. So this is the structure of D. So next question arises, what happens if D becomes 0 or deeper becomes 0? Okay, so next question arises in our mind that what will happen? Suppose that this is our structure. Suppose this was D, but it becomes 0. So in totality, what is left? This is only deeper is left. If D is 0, what we left with? We left with only D per. Okay, deeper. If D is 0, we get deeper. Okay, if D is 0, we get deeper in this case. And when there is only deeper in our case, when there is only deeper in our case, suppose this is deeper. So when we apply J, this will become J deeper. Okay, so this is the case of these types of submanifolds are known as totally real submanifold. Totally real. Okay, next case is when deeper is 0. Suppose that deeper it becomes 0. So we have, in this case, we have only D will be there. Invariant part, and there will be nu in this case. So this type of submanifolds are known as complex submanifold, or we can say complex manifolds. Okay. So these are certain types. It is already mentioned in the this slide also. When D is 0, this will be a totally real, and when deeper is 0, this will become complex. Next comes the semi-slant submanifolds. So what is semi-slant submanifold? Let me again go to our one of the slides. So what is semi-slant? When we say that semi-slant, again we will try to make it as a diagram. So let's suppose that this is TM. This is TM. Suppose that this is TM. Suppose that this is TM, tangent space of M, and this is normal space of M. Okay, let's suppose that. When we are talking about semi-slant, so this means that there is invariant part and there is a distribution which is slant. Okay, so this is known as semi-slant. Slant, what is basically slant distribution? So when we apply J on slant distribution, okay, so it has some parts in this itself and some part will move on to this part. Okay, there will be some part will be in this J d theta will be in some part. Some of the d theta will be in Tm per and some will remain in Tm. Okay, that's why if suppose that y belongs, Yes.
Your screen is not visible for us, so please share
Okay.
it.
Let me again share the screen.
Okay, sir.
Is it shared now?
It is in the process.
Yeah, it's
Shared now. So we were talking about semi-slant submanifolds. In semi-slant submanifolds, there are two distribution in tangent space. First is D1 and second is D2. D1 is basically invariant. Invariant means if we apply any operator, whether it is J or phi, it does not change its space. It does not change its region. Okay. And what is D2? In our case, D2 is slant distribution. So what is slant distribution? Slant distribution means when we apply J, it will move certain and it will not go directly to normal or nor it will be in this space itself, tangent space itself. Okay, so it will behave like this. For example, these are manifold, submanifold. Let's suppose that this is our submanifold, and there is a vector. This is our submanifold, and suppose that these are the vectors. Okay, these are two vectors, or there is only one vector. So what is slant? Slant will be, let's suppose this is V is a vector and we apply J on this. So this will be JV. It will move by certain angle, and this angle is known as rectangular angle or slant angle. Okay, so it will move with a slant angle. It will not move. Previously in CR we saw that when we apply J on this, it will move orthogonally to normal bundle. But in this case, it will not move orthogonally. Some part will be there. Okay, so this type of manifolds are known as CR submanifolds. Okay, then again there will be a question: what happen if D becomes 0? If this part becomes 0, if this part will become 0, so that means in tangent space we are left only with, suppose that we are only left with, this is our manifold, suppose that D is 0, so in tangent space we are only left with D theta, and in normal we have T ampere, normal bundle. This is tangent bundle. Okay, so there will be some J deeper will be there, J d theta, some part of J theta will be there. Okay, so this type of submanifolds are known as slant submanifold. Let's have the definition. Okay, there will be a distribution. Theta will be the angle between x and jx. Okay, x and jx is the angle between them is represented by theta, and that is known as slant angle. And we can deduce that this cos theta will be this one. Okay, since we know that dot product is, we already know that dot product between any two vectors. We know that dot product between, suppose that this is A is one vector, B is another vector. So we know that product of these two vectors is mod A, mod B, and cos theta. When we generalize this concept, you will get this part. Cos theta will be inner product of some jtx and tx, and it will be the magnitude of jx and tx. It came from the simple dot product. Then again, certain question will arises when we are doing this type of problem. Suppose that there are some, let's hope that there are no, only d theta is not there. There are two thetas are there in the distribution. Suppose that d1 and d2 are both slant. So what will be the study? How we can study these types of, what would be the geometry of these submanifolds? So another submanifold was discovered, or the notion was given, and that notion is known as bi-slant submanifold. Okay, so that was bi-slant submanifold. So bi means two. Slant means, we know that slant means it has some angle. Okay, so that's why that was known as bi-slant submanifold. Then comes hemislant. Let me give you the definition of hemislant. What is basically hemislant mean to us? So basically, in hemislants submanifold, which we study, there will be three distributions. Earlier, there were only two distributions, and particular cases were where one of them was zero. We will get some particular submanifolds. Now we have three distributions, and D, where D tangent. This TM, you should know. This is TM is basically tangent space of M. Okay, so this is comprises or it has three distribution. First is D, second is D theta, that means the slant distribution, and this is anti-invariant distribution. Okay, so it is written in the next part, that is distribution D is invariant, D theta is slant distribution, and D per is anti-invariant. So let's try to understand the geometry of this submanifold, how it look like, and what will be the effect when we apply some operators on these manifold. Let this, suppose that this is our, suppose this is our M. So it has some tangent space. Let's suppose this is tangent space of M. This is normal space of M, T per M. Orthogonal. These are orthogonal spaces. We know that. Suppose this is our curve. Then suppose there is a tangent, and this point, if orthogonal to tangent is basically what is known as normal in geometry. We know that. If it is orthogonal to this tangent, this is normal. So normal came out from the tangent. All the collection of all the orthogonal vectors to tangent gives you the normal. So these two are orthogonal to each other. Okay, so we are talking about, we were talking about quasi-hemislant. So in this case, it is D means invariant. This is D theta. That means when we apply J on this or phi on this, it has some component will be left there, and some will goes to Tm per, and the next is D per. So when we apply J or any operator, J is just an operator. We can use also phi. When phi is using, when we use phi is when we are using ambient manifold is basically our scalar manifold. Once we are using ambient as a Sasakian, we will use, in place of J, we will use phi. Okay, we will discuss later in the later sections. So when we apply J on this, it will go to this distribution. It will form there. And when we apply J to this, some part will comes to this distribution. Some part, not whole D theta will be there. Some part of D theta will be here. And there is an invariant part also in this case. Okay. So when we apply J to D, this will be in Tm. It will not go anywhere. It will be a part of D, or we can say this will be equal to D itself. Okay, this will be D itself. When we apply J to D theta, it will be break into two parts. Okay, some part will be in tangent space, and some part will goes to normal distribution. And when we apply J to D per, the whole part will be in Tm per. So this is the geometry, and you have to use when you are doing calculations in geometry. Okay, differential geometry. When you are using some research papers. Later on, I will share one of the research papers, and we will do some calculations. And meanwhile, let's move to the next topic. So this was quasi hemislant. Then our main topic, that is quasi bislant. What is quasi bislant submanifold? Earlier we are taking Sasakian as an ambient manifold. We will discuss this submanifold taking Sasakian as an ambient manifold. Okay, so in this case, tangent space is decomposes into these part, that is D. D is our invariant part. D1 and D2 are both slant, and there is a vector, additional vector xi. Since we know that Sasakian is an odd dimensional manifold, so there will, whenever there is an odd dimension, that means it should have of the type 2m plus 1. Okay, that 1 is basically given by this vector itself. Okay, this is comprising 1. So whenever we have contact manifold, this xi or this is just a symbol we are using for a vector. Okay, so whenever there is a contact manifold, this will be there in every manifold. Meanwhile, we are discussing quasi-Bieslant submanifold for Sasakian manifold. So this is the basically geometry of our submanifold, that is quasi-Bieslant. Okay, so what is quasi-Bieslant? Let me again draw the diagram for this. Okay, we have some, this is our submanifold. This is Rm. Okay, so in this case, we have D, we have D1, we have D2. Okay, this is T ampere, and this is Tm. Okay, so when we apply J or phi, we will apply 5. Okay, since we are talking about Sasakian, whenever there is Sasakian, this operator should be taken into consideration. Okay, so this will be D itself. And when we apply phi on D1, it will be subset of D2. And when we apply D phi on D2, it will be subset of D1. That means when we apply this one, so some part of this will come to this D1 and it will become phi D2. And when we apply D1, this will goes to this D2 and some part of this will be phi D1. Okay, so this is the geometry. It is written here also. It's third part. Phi D1 is orthogonal to D2 and it is a part of D2, and phi D2 is orthogonal to D1. Okay, the distribution D1 and D2 are slant distribution. Okay, so this was up to this was the basic concepts which we should know before we are putting hand on some of the question research papers on manifold theory and basically on quasi-Bieslant submanifold. When you are going to solve a paper on quasi-Bieslant submanifold, you should, these are the basic concepts you should know before you are going to solve this paper. So why I choose this quasi-Bieslant submanifold? It was one of my student of post-graduation. She came to me, she approaches me and she said that I have to submit a project on MSc project, post-graduation project. Sir, kindly give me some topic regarding her dissertation. So I gave her this quasi-Bieslant submanifolds. And she comes with this paper, and later on we discuss this paper, and soon she will definitely give some good result on this quasi-Bieslant in light-like submanifold basically. Okay, so we will discuss it later. So coming back to the paper, we have this. There is one paper written by Pradeep sir. It was published in Arabian Journal of Mathematics, and the author was Pradeep sir was there. Rajendra Prasad were there, and Sandeep Kumar were there. It will be I have given the in also refer in the reference section, mentioned in the reference section. So before going to the results, let me share some basic results which we should derive in order to get the integrability, concept of integrability, and we will discuss two concepts in this session. The first one will be the concept based on integrability of distributions, and later on we will also discuss totally geodesic foliations. So these two topics we will cover in today's lecture. Okay, so let me again go to the writing pad. So as now let me draw again what is quasi-Bieslant. Quasi-Bieslant. bislant. Bislant submanifold. So when we are talking about quasi-bislant submanifold, so there are three distributions in TM, tangent space. So one is D, another is D1, and last one is D2. Okay, so and this is for tangent space of M. This is M and this is normal of M. Okay, this space is normal of M. So whenever we have to there is an element of, suppose that this capital X belongs to this TM. Capital X is an element of this tangent space, so it should be belongs to one of them. So what will we do? We have a projection of X on TM. It is given by projection of X on TM is given by, since we cannot say that this X belongs to D1, this X belongs to D2 or D. Okay, so there is a projection of this X. So X can be written as Px means some part of X belongs to D. Qx means it is representing D1 and D2 is represented by R. Okay, so there is another additional vector, xi we are talking about. There will be in tangent space, there will be some xi also. This is D1 and this D2 and this is our xi, which was we were talking about additional vector. Okay, characteristic vector is this one in our case. So this X can be written as, since there we have these distribution in tangent space and X belongs to tangent space. So this is basically Px plus this is for, this implies that this belongs to D. This is an element of D. And this is Qx. It will represent that this will be, when there is Q, this means that it will represent, it belongs to D1. And I think it was Rx. Then Rx is basically, it belongs to, this says that this will belongs to D2. And we have also eta. We have eta also for this additional vector, characteristic vector. Okay. So we have eta of X also for xi. Okay. Xi is there. So this will be eta of xi. So you can see in this one. Okay, so whenever there is X, we have to write, every tangent space can be written in form of this right hand side. Px means component of D, Qx means component of D1, R means component of basically D2, and eta is xi means component of xi. Okay, so coming to back to this division, whenever we apply phi on any tangent vector, this will be split into two parts. One part is tangential and other part is normal. Okay, Tx is the tangential part, Nx is the normal part. Tx and Nx. Tx plus Nx will be there. So this is basically tangential part. This is tangential part, and this is normal part. Okay. Whenever phi is applied on X, it should be split into two parts, that is Tx and Nx. Okay. So what will happen if we apply, if I again apply phi on this phi X? What will be there? So we know that phi X is equal to Tx plus Nx. So this phi will be operated on these two. Phi will be operated on this Nx. Okay. Since this is tangential. Okay. And every tangential can be written, when we apply phi on tangential, it will be break into T and N. So this will break into Tx plus N of Tx. Okay, and there will be phi of nx. And phi into phi, it will give you phi square x. Okay, so you should know what is phi square in Sasakian. So let me go back to the screen, and we have a definition of Sasakian. Okay, so we know that this v phi square, it is so symplectic, still it will satisfy these conditions since it is a contact metric structure. For a Sasakian is also having contact metric structure. So we know that phi square is minus I plus eta x xi. So we will use this definition in our case. Okay. In our case. In our case, okay. So this will be minus x plus eta x xi, and this will be equal to t square x plus n into tx plus phi into nx. So this will be one result. Okay. Similarly, if y applied to this part, if we apply phi on this part, this equation we say, so we will get, what will we get if we apply phi on this? If we apply phi on this, so this will be phi here, this will be phi here, this will be phi here also, and this will be phi. And we know that phi on xi will be 0. We know that phi xi is 0 by using structure of contact. Sasakian is also having contact structure. Convexo is also having contact structure. O-symplectic is also having contact structure. Okay, that's why it is, that will be 0. So when we solve this, we will get these two conditions. Okay. So what is basically happens to this? We apply phi on this x, so it will break into tx plus nx. Okay, and we just compared the tangential and normal part. Let me derive this part for you. So let me write again what was given to us. Suppose it was given that x, it was given that x is equal to, hello? So it was given that x, it was given that x can be written as px plus qx plus rx plus eta x xi. Okay, when we apply phi, it will become phi x, it will become phi px, it will become phi qx, and this will be phi rx plus, when we apply phi on this, it will become 0. So this will be 0. Okay, and we know that phi x is equal to tx plus nx. You can see here phi x was tx plus nx, and similarly we will derive this expression. Since this is t, so this will be t px only. Okay, this was element of d theta, it will changes into tqx plus nqx. Similarly, rx is again part of theta, this will be trx plus nrx. Okay, so when we compare tangential, there is tangential, this is tangential, this is tangential, this is tangential. So by comparing the tangential component, we will get these results. Tpx is equal to nqx. Okay, these are the main important parts of Gauss and Weingarten equation, which we are using in these papers. Okay, we have to use results in these papers. Okay, and these are certain lemmas which we use in our paper. And there is a concept integrability. Let me Okay, so these are the theorems which we have to, which we are using in the coming sessions in the next paper. Integrability of distribution. This was another theorem on, since we have three distribution D1, D2, and D3. So we will find the integrability condition on these three. Okay, so
Excuse me,
this
Professor.
is yes.
Professor, kindly conclude your work. Actually, we have more presenters.
Okay.
And we have to finish
Okay.
it by 12.
Okay, sir. I'm
Okay, sir.
concluding it. Okay.
Thank you so much.
So, there are certain integrability conditions, theorems. We have to look into this, and this is a theorem for foliations. There are certain theorems on foliation. These are the references you can go through, and this was one of the we can say building block of contact manifold. If anybody want to get the knowledge of what is contact manifolds, he or she should read this book. This is very important book for contact point of view. And these are certain some of the references we can look into. I think this is from my side. If you have any query regarding this, you are welcome. Any query regarding this part?
Thank you very much, Dr. Arvind Massey, for your nice speech for us and your presentation. Just if there's questions, participants, please reply with the chat box. If no question, just according to our plan that we have to hold today, this time now, paper presentation ID 21, Dr. Rupal Shroff, Assistant Professor, Department of Mathematics, Dr. Vidros D. Card, MIT, World Peace University, India. His paper entitled with graph derived from idea of lattice. So please come with us, dear presenter.
Yeah, good morning, everyone. Am I audible?
Yes, ma'am.
Yeah. Is my screen visible?
Yes, ma'am, visible. It's processing.
It's visible.
Yeah.
It's visible, ma'am. Please continue your presentation. Thank you, ma'am.
Yeah. Okay. Good morning, everyone. Title of my presentation is Graph Derived from Ideals of Lattices. This is joint work done with my PhD student, Mrs. Pratibha Shirsagar. These are the outline of my presentation. Basically, I have divided in 5 parts. Main results we shall be discussing in the 4th section. So the graph derived from ordered structure, algebraic structure is a hot topic of study nowadays. From last 2 decades, this has been studied extensively by many researchers. In this, the initiative was done by Beck in 1988. He defined zero divisor graph of commutative rings to establish connection between graph theory and the commutative ring theory. Later on, many authors like Halas, Zult, Nimborkar, Pasadikar, Joshi have studied different type of graphs over the algebraic structures like semigroups, rings, and ordered structures like lattices, posets, and cosets. There are various type of graph defined like zero divisor graph, co-maximal graphs, then essential ideal graph, essential element graph are studied by various authors for algebraic structure and ordered structure. Recently in 2022, Abdul Qadir introduced maximal ideal graph over a commutative ring. They defined the graph MGR, maximal ideal graph, as an undirected simple graph whose vertices are all non-trivial ideals of the ring, and the two ideals or two vertices are adjacent if their addition I plus j is maximal ideal of the ring. They studied some basic concepts like diameter, girth, click number, and they derived necessary and sufficient condition for this graph to be a complete bipartite graph. Further, this same concept, maximal ideal graph, is generalized over the semi-rings by Abdul. He investigated planarity, click number, cut vertex, etc. for maximal ideal graph. So before I go for a main result, I would like to just recall some basic concepts from the graph theory. Just like graph, what is a graph? Graph is a triple consisting of a vertex set, edge set, and a relation that associate each edge with two vertices. Graph is called a simple graph if it has no intersecting edges, multiple edges, no loops. It is connected if there is a path between every two vertices. Graph is called complete graph if there is an edge between every pair of vertices. We define a bipartite graph if the vertex set of the graph can be partitioned into two as V1, V2, disjoint sets. Okay, it is called complete bipartite graph if every vertex of V1 is adjacent to each vertex of V2, then we call it complete bipartite. Okay, a path is a sequence of vertices and edges. None of them is repeated. In a cycle, it is also a sequence of vertices and edges. It is a path where the end point and initial point, final point are same. They are coincident. Okay, the length of path or a cycle is number of edges appearing in path cycle. Now, let us talk about distance. Distance between two vertices is denoted by d of AB. It is length of the shortest path containing it. Based on the concept of distance, diameter of graph is defined. This distance is calculated for any two vertices. Diameter is for the whole graph. It is the supremum of distances between any pair of vertices. Girth of a graph is denoted by G of G. It is the length of shortest cycle. We talk about the cut vertex. Cut vertex is a vertex. If you remove it from the graph becomes disconnected. Okay, and planar, a graph is planar if it has no intersecting edges. Click is a complete subgraph of a given graph. Okay, and click number, the number of vertices in the largest click, it is denoted as a click number for a given graph. Chromatic number is denoted by chi of G. It is the minimum number of colors required to color the graph in such a way that each two adjacent vertices take the different colors. Next is let us talk about some basic concepts from lattice theory also. So first, lattice is defined over a poset. So what is a poset? A poset is a set with a reflexive, transitive and antisymmetric binary operation defined on it. Okay. Supremum is the largest element of any given poset. Infimum is the smallest element of any given poset. Now, a lattice is a poset in which infimum, that is smallest element, and supremum, that is largest element, exist for every pair of elements in L. Then it is called a lattice. Lattice is bounded if lattice contains the smallest element 0 and the greatest element 1. 0 and 1 are just notational convention here that has nothing to do with actual 0 and 1 numbers. Okay. Now, distributive lattice, this we call as distributive identity. A meet B join C equals to A meet B join A meet C. If every element of lattice satisfies this identity, every pair, triple of the elements of L, then it is called a distributive lattice. Same, this is called as modular identity for lattices. If for every A less than equal to C, modular identity is satisfied by B element in L, then it is called a modular lattice. Now, I'll talk about the main thing, that is ideal. Ideal is a non-empty subset of the lattice, which is closed under the operation join. And for every x which is smaller than the element A of ideal, x is contained in the ideal itself. That means it contains all the elements lying below any of the elements of ideal. Further, the collection of all ideals of a lattice forms a poset under the set inclusion. Moreover, it is a lattice. Okay, and if your lattice L is a bounded lattice, then this ideal, the collection of all ideals of a lattice, becomes a complete lattice. Now, types of ideals: proper ideal, a proper ideal, maximal ideal. Proper ideal of a lattice L is maximal if it is not contained in any other ideal. It is not contained in any other ideal of the lattice. We denote the set of all maximal ideal by this notation, max max of L. On the same lines, minimal ideals can be defined. Minimal ideal is an ideal which do not contain any other ideal. Okay, so these are dual concept of each other, maximal and minimal. We denote the set min of L as the set of all minimal ideals of given lattice. Jacobson radical, we define Jacobson radical as the intersection of all maximal ideals of the lattice. Now, if your lattice is distributive lattice, then the ideal lattice, I of L, is also a distributive lattice. Now, throughout our results, we have considered lattice to be a bounded lattice. It consists the least element 0 and the greatest element 1. Coming towards our main result, this is our definition of the graph. We define maximal ideal graph for a bounded lattice. Okay, so what is maximal ideal graph? We denote it by mg of L. This one, this is the notation. It is an undirected sample graph. The vertex set of this graph is the collection of all non-trivial ideals of L, and two distinct vertices, say I1 and I2, are adjacent if they are joined. I1 join I2 is maximal ideal of the lattice. This is we are calling as maximal ideal graph. Now, for an example, I have taken this lattice. It is bounded as the least element 0 is here, 1 is here. Okay, I have collected all proper ideals, non-trivial ideals of the lattice. There are 4 ideals. As the lattice is finite, every ideal is the ideal generated by some element. Okay, so I have 4 ideals, 0A, 0B, 0ABC, and 0BD. This one, this. Okay, after that, we have found out the maximal ideals. Maximal ideal is this one, 0ABC and 0BD. I3 and I4 are maximal ideals. After that, we collected the join of each ideals. I1 joined with I2, I3, I4. I2 joined with I3 and I4. And I3 joined with I4. Then we checked which of these is going for maximal ideal. We could found that I1 join I2 is I3 maximal ideal. So I1 join I2 are connected over here. I1 join I3 is I3. So I1, I3 are connected here. Okay, that way the graph is constructed. You can see this is a connected graph. Okay, now coming towards some basic remarks about this. So every non-maximal ideal, or rather I'll say every non-trivial ideal of a lattice is either maximal or it is adjacent to some maximal ideals. Then no two maximal ideals are adjacent in this maximal ideal graph, because the join of maximal ideals becomes the lattice itself, which is not a non-trivial maximal ideal. Okay, this will be because of this fact that every two maximal ideal are not adjacent, we will have non-adjacent pairs in the graph. That's why this MGL will never be a complete graph. Okay, further, next we have found out if there is a maximal ideal K belonging to max of L, K belonging to max of L, if it is adjacent to I, K belongs to Ni intersection Nj, Ni and J are neighborhoods here. So K is adjacent to I, K is adjacent to J. It is possible only if K is adjacent to join of I and J. Okay. Further, we extend the results considering two non-trivial ideals, non-trivial ideal I and J of lattice L. If this Ij are not maximal, There exists a maximal ideal K which is adjacent to both I and J. Okay, so we have given a condition of isomorphism. This MGL is isomorphic to complete graph Kn or bipartite graph Kn1 for n greater than 2. Then the lattice has unique maximal ideal. We have got the proof of this, and the example for this is here. This is my graph. What we have done is we have considered this A, B, C, D as the ideals, non-trivial ideals of the lattices, which are posed over here. You can see. Okay, and this is the complete graph with 4 elements. We have tried to find out the lattice of this, which is here, in which you can see clearly the maximal ideal is the ideal 0, A, B, C, and D. It is only one maximal ideal. Okay. Now, for other part, K31, I have considered this star graph. Okay. We tried to find out the lattice corresponding to this under the maximal ideal graph condition. So we have got this one as our lattice, or vice versa also. If we try to find out the graph of this particular lattice, it goes for this one, star graph. Okay, where you can see, you can make the set of vertices as ABC one set, D as another set, and it is a bipartite graph. Okay, so these are two examples. Further, we investigated that if lattice is a chain with 0 and 1, that is bounded one, okay, then the graph, maximal ideal graph, is a star graph. Okay, next is the Jacobson radical is taken into account. Consider a lattice L whose Jacobson radical is non-empty, non-zero, right? It is non-trivial and it has more than 2 or more maximal ideals. Then there exists a subgraph G1 of maximal ideal graph obtained by taking vertex set V as union of V1 and V2, where V1 is collection of all maximal ideals of L and V2 is the collection of ideals which are contained in Jacobson radical. If we form a graph like this, under the condition that Jacobson radical is non-zero, ideal has more than 2 or more maximal ideals, then the graph becomes a complete bipartite graph. Okay, now further, if Jacobson radical is non-zero, MGL is complete. The maximal ideal graph is complete bipartite graph if every proper non-maximal ideal is contained in L. So the thing is, what we have in this corollary, what we have altered is, instead of taking V2, we have defined the lattice in such a way that V2 will contain all the ideals other than maximal ideals. Okay, and that becomes exactly complete bipartite graph then. This is the example over here. If you can see, this is my lattice. We have collected all the proper ideals I1, I2, I3, I4, I5, I6. Maximal ideals are I5 and I6. This is ideal generated by E and ideal generated by F. Then we collected their intersection, I5, I6. The intersection goes for this ideal generated by D, which is non-zero. And if we see here, the graph formed here is this much. Okay, so what we have done is collected all the ideals which are contained in Jacobson radical. So that will be I1, I2, I3 and I4 that are contained in GL. So I made the set V1 as the collection of maximal ideal I5, I6, V2 as the collection of I1, I2, I3, I4, and we get a complete bipartite graph for this. Then coming towards next result, a lattice L such that every two maximal ideal of L has non-zero intersection. Okay, then the graph MGL is connected and its diameter is less than equal to 4. This result is considered in different 5-6 cases and we have come up with this one, diameter is less than equal to 4. Moreover, if we impose the condition of modularity on the lattice, the diameter reduces to 2, less than or equal to 2. If I add a condition that lattice is modular, then the diameter is less than equal to 2. Okay, further, based on this theorem, we can give a remark: the intersection of any two maximal ideal is 0 if the maximal ideal graph if the intersection of any two maximal ideal is 0, then the maximal ideal graph may be connected, may not be connected. We have got example in both the cases here. The first example is here. Consider this lattice. Okay, we have found out all the proper ideals, which are I1, I2, I3, I4, and I6. Okay, out of it, maximal are I4, this one, ideal generated by D, I5 generated by E, I6 generated by F. Okay, then we checked I5 and I6 intersection is 0. I4 and I6 intersection is 0. And look at the graph, maximal ideal graph, it is disconnected. Now I'll give example. In other case, I have got the connected graph also. Okay, sorry, I forgot to include it here. Yeah, the next coming towards, if the Jacobson radical is non-zero, then the girth of the maximal ideal graph is 3, 4, or infinity. Okay, further, if every two maximal ideal of a lattice have non-zero intersection, then M is a cut vertex of maximal ideal graph. Then the cut vertex is equal to intersection of any two maximal ideals. This is the result. Okay. Now, next is the proposition. Same condition we are imposing. The lattice is bounded lattice with the Jacobson radical non-zero. Then the maximal ideal graph is planar. Then the cardinality of, that means the lattice has max 4 maximal ideal at the max. Okay. Coming towards the results which are based on distributive lattices. If I am imposing a condition distributive lattice with 1 and ij be two ideals of L. If M is a maximal ideal, then see, I have considered two ideals I and J which are non-maximal, okay, such that their intersection is contained in maximal ideal. Then one of them is contained in maximal ideal. Further extending, if there are two ideals I1 and I2 of a bounded distributive lattice, such that their intersection is non-empty, then at least one of them will be an isolated vertex. So the graph is going to be disconnected here. Okay. Further, considering a lattice, distributive lattice with two or more minimal ideals and two or more maximal ideals. Okay. The vertex set MGL will be equal to union of minimal ideals and maximal ideals. If we define vertex set like this, then the graph is split and the click number is either minimum of L, the cardinality of the number of minimal ideals, simply I can say, or the number of minimal ideal plus 1. So for this one also we have got an example here. This is the distributive lattice. We have tried to found out its graph, and after finding the maximal ideal graph, we said that vertex set is here exactly union of minimal ideals and maximal ideals. And the click is here I1, I2 and I3. Click number. Okay. So this is the maximum click. The click number is 3, which is equal to the number of minimal ideals. And another way, minimal plus 1, where we get the number of minimal ideals plus 1. This is the example. This is also a distributive lattice where we have defined the vertex set to be the minimal ideals union maximal ideals. Minimal ideals are ideal generated by A and ideal generated by B, I1, I2, where maximal ideals are ideal generated by C, collection of ABC, and ideal generated by D, collection of 0. This A will not be here. It is only 0 BD. Okay. So we got the click number as minimal number of minimal ideals plus 1 here. Yeah. The another one, why distributivity is necessary in that particular result. We have got a non-distributive lattice where the click is not equal to the number of minimal ideals, nor it is plus 1 of that. Okay, just see the example. The minimal ideals are I1, I2, I3, ideal generated by A, B, and C. Maximal are I4 and I5 generated by D and E. The vertex set V is the union of minimal ideals and maximal ideals. But what is happening? I1 and I2 are not adjacent here. Sorry, I1 and I3. These two are non-adjacent, right? Okay. That is why minimal of L is not a cliff. Okay. Further, L be a distributive lattice, same bounded distributive lattice. If we take vertex set as union of minimal and maximal ideals, and the number of minimal ideals are less than equal to 3, then the graph is planar graph. The earlier bound was 2, here the bound is 3. Then it becomes a planar graph. Okay, this is the final result. These are my references I have used. Yeah, that's all from my presentation. Thank you very much, organizers, for giving me an opportunity to present my work. And thank you very much, audience, to listening patiently.
Thank you, ma'am, for your nice presentation and interesting work for this conference. Now, just it's time now for discussion. Now, I am requested to the participants to discuss with her, and you have to write some query that you have in chat box.
Good morning, ma'am.
Yeah.
Can you suggest any real application of your work?
Sir, I am working on it. Definitely, actually, what is happening nowadays, people are studying a graph derived from many different structures, but the lacuna is application only. So recently, we have started working on it also. Maybe in next few days, I'll be able to answer that.
Okay, no problem. Thank you so much.
Any
Any
other
question?
Yeah,
There any
hello, ma'am.
suggestion?
Yes, I do have one question.
Yes,
Yeah,
sir.
please.
My question is, what are the new educational incentives you want to add for mathematicians?
Sorry, I didn't get it. Can you please repeat?
What are the new ideas or the new concepts you want to add for mathematicians?
New ideas, see, I'll suggest there are n number of application is clinical biology of graph theory and as well as lattice theory in computer science, medicinal sciences. Nowadays, so many people from computer science are working on it. So we can move on to that because being a mathematician, our basic knowledge is much more better than those people. Right. So in my university also this happens that for basics of mathematics, they are coming to me. So I'll suggest why should not we go for it?
Okay, thank you.
Thank you all for your nice interruption with her. Now let's start the second presenter, Dr. Marj Furkan, Assistant Professor, University of Polytechnic, Algar Muslim University, Algar, India, for his paper entitled with Common Solution of Split Null Point, a Split Variational Inequality and Fixed Point Problem for an N-expansive semigroup. Sir, welcome for your presentation.
Thank you, sir. Am I audible, sir?
Yeah, you are audible, sir.
Is my screen visible?
Yeah, it's visible.
Okay, sir. Thank you.
Thank you.
So, my name is Dr. Mohammad Furkan, working as Assistant Professor of Applied Mathematics, University Polytechnic, AMU. The title of my talk is Common Solution of Split Null Point Problem, Split Variational Inequality Problem, and Fixed Point Problem for a non-expansive semigroup. Basically, in this paper, we develop and analyze an iterative scheme to approximate a common solution of split null point problem, split variational inequality problem involving strongly mapping, and a fixed point problem, which is for a non-expansive semigroup in the setting of real Hilbert spaces. Further, we deduce some special cases from our main convergence result, and in this sample, we present a numerical example to analyze the applicability of our proposed method. So this is the introduction part. This is what we have assumed throughout this paper. We are assuming H1 and H2 as two real Hilbert spaces with the usual inner product and the induced norm. We are also taking C1 and C2, their respective non-empty closed and convex subsets. In 2011, Modafi introduced split monotone variational inclusion problem. In short, we call it SMVIP, which is to find a point P in the Hilbert space H1 such that this inclusion first holds. And the image of this solution P under the bounded linear operator capital Q, which we are denoting with small q here, it is the solution of this inclusion second. Here B1 and B2 are multivalued maximal monotone mappings. F1 and F2 are two nonlinear mappings. Above split monotone variational inclusion problem comprises several problems as special cases like split feasibility problem, split zero problem, split fixed point problem, and split variational inequality problem. These problems have been studied by a number of authors over a period of time and has many uses in many real-life problems like inverse problems modeling, sensor networks in computerized tomography, data compression and radius therapy, and all that. If we set F1 and F2 as zero mappings in the split monotone variational inclusion problem, then this problem reduces to split null point problem, which is to find a point P in the Hilbert space H1 such that zero belongs to B1P and its image under the operator Q solves this inclusion. Fourth means zero belongs to B2Q. When we look separately at these problems, so 3 and 4, basically it is a pair of two split null point problems, and the image of the solution of the first problem becomes the solution of the second problem. We are denoting by omega the solution set of split null point problem. In 2012, Birne and his co-authors developed and analyzed this scheme to approximate a solution of split null point problem. They basically proved a weak and a strong convergence theorems to approximate a solution of the above problem, split null point problem. In 2013, Kazmi and Rizvi developed this iterative method, which we are denoting by relation 5. They, under some certain condition, they proved a strong convergence theorem to find a common solution of fixed point problem and split null point problem. Yes, this is very, very important and very basic definition of fixed point problem for a non-expansive mapping A, which is to find an element R in the Hilbert space H1 such that this equation 6 holds. This is the definition of non-expansive semigroup. So we are taking a family R, which is the collection of all AR, where R is a non-negative real number. So we call this family R non-expansive semigroup if the four properties hold. We are denoting by FR the set of all fixed points of the non-expansive semigroup R, and which is at the same time coincides with the intersection of fixed point sets of AR where R is a non-negative real number. So our fixed point problem in case of non-expansive semigroup looks like this, which is to find a point P in C1 such that P belongs to FR. This is a fixed point problem for non-expansive semigroup. So we are taking up this problem in our present discussion. In 2008, Klubting and Panpeng developed this iterative method, which we are denoting by 8. They basically solved the fixed point problem for a non-expansive mapping group, for a non-expansive semigroup. This was their iterative scheme. In 2012, Sensor and his co-authors introduced a split variational inequality problem, which is to find a point P in C1 such that this is one of the variational inequalities. So they basically introduced a pair of variational inequalities such that the image of the solution of the first variational inequality is the solution of the second variational inequality. Here Psi1 and Psi2 are two non-linear mappings. We are denoting by phi the solution set of this split variational inequality problem. In 2015, Wen and Chen introduced this iterative scheme, which we are denoting by 11. They basically proved a strong convergence theorem to approximate a common solution of the split null point problem and a fixed point problem for a non-expansive semigroup. At the same time, they also proved that the common solution of the above problem is split null point problem and split and fixed point problem for a non-expansive semigroup is the unique solution of this special type of variational inequality problem. If in the above scheme, in this scheme, if in above scheme we take k to be equal to 1, if here in this scheme, if we take k to be equal to 1 and B becomes an identity mapping, AR becomes a non-expansive mapping, then this iterative scheme reduces to that of which was initially introduced by Bill and his co-authors in 2012 and was later applied by Kazmi and Rizvi in 2013. Hence, motivated and inspired by the above ongoing research work in this direction by Pilupting and Panpeng, Birne and his co-authors, Kazmi and Rizvi, Wen and Chand, and other research work in this direction, we are introducing a new iterative algorithm to approximate a common solution of a split null point problem, a split variational inequality problem, and a fixed point problem for a non-expansive. So this is the preliminaries part. This is very basic definition. I am not going into the detail. This is the definition of monotone mapping. A on the Hilbert space H1, non-expansive mapping. If it satisfies this condition for all the elements for a pair of elements in the Hilbert space H1. This is the definition of firmly non-expansive mapping. Xi is strongly monotone mapping. Xi inverse is strongly monotone mapping. We are taking all of them into account while proving our main convergence theorem. Yes, this is also a very basic definition of metric projection, and sometimes we characterize the metric projection by this inequality 12. This is the definition of same monotone mapping, but in the context of multi-valued mapping. If this condition holds, then this is here we are taking B1 as multi-valued mapping, so it is said to be monotone mapping if this inequality holds. And we call B1 maximal if its graph of this maximal monotone mapping is, we are denoting with GB1, and its definition is like this. So we call this monotone mapping B1 maximal if its graph is not properly contained in the graph of any other monotone mapping. So this one is the definition for dissolvent operator J lambda B1. This is the usual remark, so I am not touching it. So this is very important definition of resolvent operator J. We are denoting it with J lambda B1. Here lambda is a positive real number and B1 is a maximal monotone multi-valued mapping. Note that resolvent operator is always single valued, non-expansive, as well as firmly and non-expansive at the same time. This is also a very important definition of an average mapping S on the Hilbert space H1. So S can be expressed in the form of 1 minus Xi. I is the identity mapping on the Hilbert space H1 plus Xi A. Xi is a real number which lies in the open interval 0, 1. Further, we notice that every averaged mapping is non-expansive mapping, and every firmly non-expansive mapping is averaged. These are some lemmas. So second lemma, you can see it is a very well-known demic closedness principle, which is uses to find fixed point. And the first lemma, in the first lemma, we are taking S and average mapping on the Hilbert space H1, A as a non-expansive mapping. So if there exists a real number in the open interval 0, 1 such that U is equal to 1 minus Xi S plus Xi A, then this mapping U is always averaged. And the composition of finitely many average mappings is also averaged. In this lemma are very important relations which always hold true in the setting of real Hilbert spaces. So these are very, very common relationships. Yes, this is the definition of OPL's condition. We generally use it to prove the uniqueness of the limit, to prove the uniqueness of the weak limit. So we are using this to prove our main convergence theorem. And the next lemma, this one, second lemma, is related to some sort of to the non-expansive semigroup, which we are denoting with R. So we are whenever we will have a relationship like this, so we can make use of this lemma. So this lemma basically we are using to establish the boundedness of the sequence of iterations generated by our iterative scheme. And this lemma is basically telling us that these two sequences, XM and SM, has same asymptotical behavior. So this lemma can be used to set a relationship among the sequences. So with above all discussion, finally, I am all set to present our main convergence theorem to approximate a common solution of split null point problem, split variational inequality problem, and a fixed point problem for a non-expansive semigroup. As mentioned earlier, we are taking H1 and H2 as two real Hilbert spaces, C1 and C2, their respective non-empty, closed, and convex subsets. We are taking Q and B as two bounded linear operators. B1 and B2 are two maximal monotone mappings. This is, as already discussed, this is the non-expansive semigroup. We also assume that the set of common solution of our proposed problems, split null point problem, split variational inequality problem, and a fixed point problem for a non-expansive semigroup is non-empty. We are denoting the set of common solution by J here. Psi1 and Psi2 are respectively theta1 and theta2 inverse strongly monotone mappings. Psi3 we are taking as a contraction mapping with the constant rho, which lies in open interval 0, 1. So this is our iterative scheme which we are taking into account. So we are taking L as the spectral radius of Q star, where Q star is the adjoint operator of Q. Q is our bounded operator from the Hilbert space H1 to the Hilbert space H2. We also assume that these 5 conditions hold. Then the sequence XM of iterations generated by our proposed iterative algorithm converges to P. P is the common solution. P is an element of the common solution of our proposed problems, split null point problem, split variational inequality problem, and a fixed point problem for a non-expansive semigroup. These are some special cases which can be deduced from our main convergence theorem. So if we set B1 and B2 as 0 mappings and Q becomes an identity mapping, then our main convergence theorem reduces to this consequence, which is to find a common solution of split variational inequality problem and a fixed point problem for a non-expansive semigroup. So I am not discussing this one as it is just an analog of our main convergence theorem. So second consequence is if we set H1 and H2 to be equal to H, C1 becomes equal to C2, Psi1 coincides with Psi.
ስለዚህ ይህን ሳምንት ክላስ ላገኛችሁ አልቻልኩም። እንግዲህ እናንተን እያጣ
Please continue, sir.
ምናልባት ቅዳሜ ከሰዓት ፕሮግራም ትይዛላችሁ?
No, Dr. Mahal.
The scheme looks like this after taking all the results into account which we have defined. So we can prove that 0 is the common solution of a split null point problem, a split variational inequality problem, and fixed point problem for a non-expansive semigroup. 0 is the common solution. So this is our iterative scheme. Finally, this is the final touch. This is the final shape of our iterative method. So now by using the software MATLAB, we plot a graph which shows that the sequence of iterations generated by our iterative algorithm converges strongly to the common solution 0, which is the common solution of our proposed problem. So this is the table of iterations for 2 initial values, -5 and 15. So you can see after 18th iteration onward, you can see our algorithm is converging faster. So after 18th iteration onward, you can see the sequence of iteration is converging strongly towards the common solution of our proposed problems. So this is the graph for the initial value x0 as -5, and this is for the initial value 15. So we have taken up 2 cases for 2 initial values. So this is what we have actually done in this paper here. Further, there are lots of motivation. Further, we can carry over, we can carry forward this work to many variational inequality problem like split monotone variational inclusion problem, split mixed equilibrium problem, and many more. So it would be an interesting brushing up if we take these problems into account to further extend the research work of this paper. So these are some references which have been used throughout this research work. So at the last, thank you very much for your kind attention and patient hearing. And thank you very much, organizing committee, to give me a chance to present my research work. Thank you, sir. Thank you very much.
Thank you, Dr. Mahad Furkan, for your nice presentation as well for your wonderful work. I am so grateful for you. And now I am requested to that participant there is some query question. You have to discuss with Dr. Mahad. Now I am requested to the participants, okay?
Okay, sir.
Yeah, Dr. Mohammed.
Yes, sir. Please speak up, sir.
Are all inner product spaces Hilbert spaces?
Actually, this is a very basic question. So maybe in order to testify my knowledge, basic knowledge, so these are very, very basic questions. Actually, all the inner product, if they satisfy the parallelogram law, then they become the Hilbert spaces. So this was not my concern, but very interesting, very interesting question.
Okay, thank you so much, sir.
Okay.
Let me ask one question.
Yes, sir. Please.
Sir Mahadi, thank you for your nice presentation, and your work is also fascinating. But I do have one question. You have used the iterative method to show the convergence of your method. Which convergence methods you have used? You used iterative methods, you know?
Yes, sir. Iterative method.
Yeah. Which iterative methods you have used?
Actually, this is a combination of we mainly have many iterative methods like Ishikawa iterative method, Man iterative scheme, Kress-Nozzle scheme, Man iterative scheme. So one is Kress-Nozzle scheme, Man iterative scheme. So generally we use this scheme, this iterative method to approximate a fixed point problem.
Okay, as I've seen this for a numerical method in a table you have displayed, after, if I'm not mistaken, after 18 iterations, you have, your method is convergent. Is convergent.
Yes, sir. Yes, sir. Yes, sir. This one.
Okay. On the 18th iteration, you have got 0, 0, 0.
Yes, sir.
Both
yes, sir.
When x is equal to -5 and when that of x naught is 15.
Yes, sir. These are two initial values, sir.
The error, is it the magnitude of the error or the answer? The last
actually here, yes, your question is very, very important and concerning. Actually, in this paper, we haven't taken out the error aspect. As we can see here after 18th iteration onwards, so error will be very, very slight. So we have taken up this discussion here. So maybe next paper onward, we can take it into account.
Okay. My question is, if the error is 0, is it possible to get the error 0 for a numerical solution?
Pardon, sir?
If this is the approximation, if 0 means totally the error is 0.
Actually, sir, your voice is not audible, sir. I'm sorry for that.
Okay. I mean that at on the 18th iteration, the error is 0, it says. Is it possible to get error 0 when we approximate a certain
yes. Now I understood your question. Actually, this is the part of approximation theory we can think of. Numerical methods are always approximating result. They always give the approximate result. So there is always an error here. So it's up to us at which extent we can minimize our error. So for this perspective, we need to take into account the estimated bound, error estimated bound.
Okay, thank you.
Okay, sir. Okay, sir.
Thank you, dear presenter and participants, for this good scholarly discussion. Now, just I am requested to that Mr. Tenau Talahun for his presentation, modified mathematical model for the transmission dynamics of COVID-19 pandemic with optimal control.
Yes, sir.
Welcome, sir.
Okay. Is that visible?
Sir?
It's processing. In the process.
Is that visible, sir?
Yeah, process. Wait,
Okay.
sir.
What about now?
No.
Wait, sir, 1 minute. You can start your presentation, Mr. Teno. It's visible.
Okay. Okay. My name is Tenau from Department of Mathematics in Mizan-Tepi University. The title of this paper says a modified mathematical model for the transmission dynamics of COVID-19 pandemic with optimal control. Now there is the outline part, introduction, methodology, mathematical model formulation and analysis, extension of the model into an optimal control, numerical simulations and discussion, conclusion and recommendation, and finally there is references. Now when you go to the introduction part, COVID-19 is an infectious disease caused by newly discovered coronavirus, and the outbreak was first identified in China in December 2019, which has been spreading worldwide. And the symptoms may appear up to 14 days after exposure to the virus. And the major symptoms of COVID-19 include fever, shortness of breath, or difficulty breathing, and muscle pain. And the novel coronavirus is mainly spread from person to person through respiratory droplets, and COVID-19 preventable through wearing face masks, using an alcohol-based hand sanitizer, and keeping social distancing. Now there is a statement of the problem. Currently, the spread of COVID-19 is the most serious health problem in the world, and being highly contagious, it has spread across the globe within months. In this study, we will try to answer the following questions: how to modify an existing mathematical model for the transmission dynamics of COVID-19 by incorporating protected and hospitalized individuals, and how to analyze the modified model of COVID-19, how to minimize the spread of COVID-19 with optimum implementation cost. Now there is objectives. The general objective of this study is to formulate and analyze a modified mathematical model for the transmission dynamic of COVID-19 with protected and hospitalized individuals. And the specific objective of this study are to compute the basic Fibonacci number of the model, to identify the most sensitive parameter of the model, and to solve an optimal control problem. Now, there is a methodology part. A deterministic compartmental model will be formulated by using system of nonlinear ordinary differential equations, and we will analyze the local stability behavior of equilibria by using Rose-Hart stability criteria and center manifold theory, and we will analyze the global stability of equilibrium by using Castro-Chaves theorem. Mathematical software such as MATLAB and mathematical user to compute and stimulate, and the numerical simulation for optimal control problem will be formulated by using forward-backward soup method. Now there is a mathematical model, that means that I use for the modifying of the given model. This is a existing model. This model developed by these two persons. Therefore, this model simply SER model. But in this model, they have not considered the susceptible individuals who are under protected and infected individuals who have been hospitalized. Now, there is a mathematical model formulation. We extend the existing SCR model by including protected and hospitalized individuals. and the model formulated using the following basic assumptions. A susceptible individual who keeping social distancing using an alcohol-based hand sanitizer and wearing face masks progress into protected class. And protected individuals cannot acquire infection of COVID-19 disease due to properly applying preventive measure. And exposed individuals could infect other people with higher probabilities than people in the infected class. Now, this is our model that simply we modify the existing model by including the protected individuals and the hospitalized individuals. That means the protected individual means which are preventive for COVID-19. That means which uses hand sanitizer, wearing face masks, and other preventive measures. And H is which is the hospitalized individual. That means the infected individual who enter to the hospitalized classes. Therefore, we add two compartments, that means the protected and the hospitalized individual for the modified model. Now, the given modified model, which is solved, expressed by using nonlinear system of differential equation with these six differential equations. Now, there is a qualitative analysis. In this qualitative analysis, there is steady state. Therefore, in epidemiology, as we know, there are two Coulomb points, disease-free and endemic Coulomb point. Therefore, in the case of endemic Coulomb points, infectious classes will be 0. Therefore, in the case of this, only the susceptible individuals and the protected individuals are non-zero, but other compartments are 0. Now, the basic reproduction number are noted is the number, the average number of secondary infection produced by a single infected individual in completely susceptible population. And we get R0, which is the spectral radius of the next generation matrix. Therefore, we get this is a reproduction number. But we can express the reproduction number, that is R1 plus R2 plus R3, where R1 is, which is the transmission from exposed individual to susceptible, and R2 from infected individual to susceptible, and R3 from hospitalized individual to susceptible individuals. Now, the existence of endemic Coulomb point, depending on the reproduction number, are not given by this. Therefore, these are the component of the endemic Coulomb point, which is expressed in terms of R0. But this endemic Coulomb point exists when R0 is greater than 1, otherwise does not exist. Because if R0 less than 1, this component is negative, but the solution cannot be negative. Instead, this is non-negative. Now, there is stability analysis. The disease-free Coulomb point E0 of the system is locally asymptotically stable if R0 is less than 1, and unstable if R0 is greater than 1. And for R0 less than 1, the disease-free Coulomb point E0 of the system is globally asymptotically stable. This theorem proved by using Castello-Chev's theorem. And the endemic Coulomb point of the system, which is locally asymptotically stable if R0 is greater than 1. Therefore, this theorem proved by using center manifold theory. Now, there is a bifurcation analysis. In this analysis, there is a bifurcation coefficient A and B. Now we get that means when we solve the bifurcation coefficient A, we get negative, which is less than 0, but B is greater than 0. Therefore, in the case of this, we get the system undergoes a forward bifurcation at R0 is equal to 1. As you see in this graph, when R0 is equal to 1, there is a bifurcation, but when R0 less than 1, there is stable disease-free Coulomb point, and when R0 greater than 1, there is stable endemic Coulomb point. Therefore, this graph indicates the forward bifurcation. Okay, the other one is sensitivity analysis. As you see in this figure, there are positive correlation with R0. That means these parameters have positive correlation with R0. This means that if this parameter increases, then the reproduction number also increases. But this theta, rho, and nu and alpha have a negative correlation with R0. This means that if this parameter is increased, but R0 which is decreased. The other one is the extension of the model into an optimal control. Therefore, in the case of this optimal control theory uses monetary and maximum principle to reduce cost by finding optimal strategies for control parameters. Now, optimal protection and hospitalization using state system we use optimal control to find protection for susceptible and hospitalization for infected that would minimize the total infected population while using optimum resources. Now, for this purpose, we define our control sets. That means in the case of this, simply the control set, this is a control set that is theta and alpha. Theta means which is protected rate, and alpha, which is the hospitalization rate, but which is depend on time, Okay, now the optimal control problem to minimize the cost functional. This is our cost functional, or which is the objective function subject to the state system that is we have in our model. Now, our objective is to find the optimal values for the control of theta star and alpha star such that which is minimize the objective function over theta alpha, an element of the control sets. Therefore, this is our objective, and this is a Hamilton. Now, for an optimal control set theta alpha that minimize the objective function over the control set, these are the Advin system that I have get for the given value. Now, this is the control set is theta star and alpha star characterized by this. Therefore, the Advin system transversality conditions and optimality conditions are standard results from Monotone maximum principle, and the optimality system formed from state system and the Advin system by incorporating the characterized control sets and transversality condition. Now we go to the numerical simulation part. We perform some numerical solutions on the modified model and the resulting optimality system. Now, in the case of this, simply we compare the control parameters and the optimal parameters. Now, in the case of this figure, cost comparison for optimal and constant control. Therefore, this is the cost of disease control. As you see in this graph, the optimal control cost, which is less than all of the constant controls. That means there is a protection rate theta. Therefore, the optimal control cost, which is less than all of the controls, the constant controls. Now, these are some graphs for optimal control of theta, exposed population comparison for optimal and constant control. Similarly, as you see, where theta is optimal control, the number of exposed population is reduced when we compare to the constant controls. Similarly, the infected population when theta is optimal, which is less than all of the constant controls. But in the case of this figure, as you see, when the contact rate increases, we need the maximum protected rate. As you see, at the early stage of the outbreak, we need the maximum protection, and which is decline over time. It is decline to 0 over time. Therefore, this is some numerical part. And the other one is optimal control for hospitalized rates. As you see, in the case of this figure, as alpha or the hospitalized rate is optimal, the number of exposed population is decreased when compared to the constant controls. And also when theta is also optimal, the number of infected population is decreased when we compare to the constant controls. But at this figure, at the early stage of the outbreak, we need the maximum hospitalization. This is the maximum hospitalization, but this is decline over time. Now, in the case of this, when both the protection rates and the hospitalization rate is optimal, the cost is minimum when we compare to only alpha and only theta are optimal. Therefore, as you see in this figure, when both parameters are optimal, the exposed population is decreased. Okay, the other one is conclusion part. In this, we have established well-positiveness of the modified model by proving the existence, positivity, and boundedness of the solution. And we have observed that the outbreak of the disease dies out if R not less than 1, and the disease endemic if R not greater than 1. Using central manifold theory, bifurcation analysis of the modified model was proven, and the model expanded forward bifurcation at R not is equal to 1. Furthermore, from sensitivity analysis of R not, we have observed that the recruitment rate and effective contact rate are the most sensitive parameters to our model. And if the protection rate increases, then all infected classes are decreased. Moreover, our analysis reveals that an optimal control rather than the high constant control is preferable. Now, based on our result, we recommend that the stakeholders should work on decreasing the positive indexes and increasing negative indexes parameters, and adherence to the computational protection and hospitalization control measures should be strict. So these are some references that I use. Okay, thank you. If you have any question, please wait up.
Thank you, Mr. Warku, for your hardworking and interesting presentation. If there is question, let's just invite the participant. So please, participants, ask him if there is question regarding with his presentation.
May I ask?
Okay, great.
No.
Yes.
Thank you for your nice work, and I really enjoyed your presentation. And I have a couple of questions. Yes?
Yes.
I think in your model, you considered the rate of spread and the transmission. Is it constant or variable? Your rate of transmission. Your rate of transmission is there, I think.
Beta is the effective contact rate. That means the rate of transmission.
Yeah. So is the rate of transmission you considered constant or variable?
In the case of this is constant, but theta and alpha are dependent on the time. For this is varied in the case of optimal controls.
No. My question is your rate of or transmission rate is constant or variable? In reality, it cannot be constant.
Yeah, you are right.
Okay, in reality, it cannot be constant, but if you consider it may be complicated, but I came across someone who has used the rate of transmission is variable, and that he has got very interesting result. Okay, look, in your slide number 10, there are a system of nonlinear equations, 3(1)a through to that of 3(1)f. These are system of nonlinear equations. What method you have used to solve these equations? When you simulated, what method you have used?
For simulation purpose?
Yeah, you have simulated,
and
we have seen many simulations. So which techniques or methods you have used to simulate this one?
OD45 solver. We use OD45 solvers.
OD45 solvers.
Yeah.
Okay, the other question is, when you say that your title is modified, you have modified the existing model.
Yes.
The existing model. But I didn't see any comparison that shows yours is better than the other. Have you compared the two models? Rather than just simulating your work, it is better if you compare your model with that of the existing one. Have you compared the two models?
Yeah, I compared, but it is
Have
broad.
you comparated in this work?
Yeah, I compared, but in this slide, due to the maximization, we reduce that part.
Okay, so it is better if you incorporate so that we can see that yours is better than the previous one.
Okay, good.
Okay, last question. Sorry.
No problem. Can continue.
Once after developing a certain model, yes, we need to validate with the existing data. Have you taken some data from some hospital or somewhere to validate? Have you validated your model, in fact?
Yeah, it is valid by showing the well posedness of the model.
No, you have shown the validity. You have validated it in mathematical.
Yeah.
If you go to some hospital and take some data, yes, from hospitals, from hospitalized COVID-19 infections, if you take some data,
I can't take due to the time limitation. I can't take that data.
Okay, or you can leave the room for the other to validate. Anyhow, it is better if you validate. Thank you for your work anyhow.
Okay, thank you for your question.
Okay, thank you, presenter and participants also. Are there any additional question?
Yeah.
Of course.
Okay. Thank you very much for your very nice presentation, Teno. I have two questions regarding to your presentation. The first one is, what is the epidemiological implication of R naught is equal to 1?
Okay, it is a nice question. Now, as I discussed it in the bifurcation analysis, when R naught is equal to 1, there is a bifurcation. Now, there is a bifurcation coefficient is A and B. When I solve the bifurcation coefficient, A, we get negative value, which is less than 0, and B is, and also B is, which is positive. Therefore, in the case of this, by using central manifold theory, when R naught is equal to 1, there is a forward bifurcation. But if the bifurcation coefficient A is greater than 0, then the result will be backward bifurcation. But in our analysis, we get the forward bifurcation.
So the forward bifurcation implies that the disease can be eliminated or not?
Through the time, it will be eliminated. That means in the case of, as you see in this figure, when R naught less than 1, there is only a disease-free equilibrium point.
Okay.
There is no endemic equilibrium point.
Okay.
When R naught greater than 1, there is unstable disease-free equilibrium points and stable endemic equilibrium points. Therefore, through time, the disease will be dies off.
Okay, thank you. Could you show me the endemic equilibrium points?
Okay. Yeah, this is the endemic equilibrium points.
Yeah, here, when you are making R equal to 1, it's, you will get only susceptible human populations. All other components are 0.
Yes.
So due to that case, you will have only susceptible populations. So it will be similar to the analysis for the disease-free equilibrium point. I hope that one.
Not similar, not
okay.
not the same, because in the case of disease-free equilibrium points, the protected compartment is non-zero, but when R naught is equal to 1, we get in the case of this P is equal to 0. Therefore, it's not the same with disease-free equilibrium point.
Okay.
Yeah.
Okay, so only susceptible populations exist in the community.
Yeah, yeah.
Okay, thank you very much. How can you interpret the disease-free equilibrium point in epidemiological view of point? Or how can you interpret the disease-free equilibrium point in epidemiological point of view?
Okay, disease-free means in epidemiology, there is no disease. There is no disease, as the name indicates.
Yeah.
But in the case of endemic, as the name indicates, there is a disease. Therefore, the main task for in epidemiology research is to mitigate or reduce the given infectious disease.
Okay. So could you show me the disease-free equilibrium point, the components of disease-free equilibrium point?
Yeah, this is the component of disease-free equilibrium point.
Yeah, in the absence of disease or COVID-19, only susceptible and protected farm populations exist in the community.
Yes.
Yeah, so it is different from the endemic equilibrium point when R naught is equal to 1. So it is a very nice one. Thank you for your very nice result.
Okay, thank you, thank you.
Thank you, Mr. Tenau and the participants also for your nice deliver for some question that you have replied. Now, just this time now, paper 24, Dr. Ram Krishna, Department of Mathematics, Government Degree College, Jammu and Kashmir. His paper entitled with Boundedness, Compactness, and Essential Norm of Product Operators on Different Holomorphic Functions in Space. Now, dear presenter, you are welcome.
So good afternoon. So my screen visible?
It is visible, sir.
Okay, okay, sir. So, very good afternoon to all. Myself, Dr. Ramkrishnan, from Department of Mathematics, Government Degree College, Karur. The topic of my presentation is boundariness, compactness, and essential norm of product of concurrent operators on different holomorphic function spaces. So first is the introduction. Operator theory is an area of mathematics and it attacks both pure and applied mathematicians in its vast area. In the last 5 decades, this area has experienced appreciable growth and many connections between the study of composition operators and other branches of analysis and mathematics have been established. So the class of composition operators is much wider than what it seems to be. They seem simple operator, but they have a wide range of applications. For example, most of the morphism between mathematical objects are weighted composition operators. Number 2 example is isometries of most of the function spaces are weighted composition operators. So there are some notations that are used throughout the paper. So let D be the open joint in the complex plane C. T is the boundary of D. Dz is the normalized area measure of D. And HD is the space of all holomorphic functions of D. And SD is the set of all holomorphic cell map on D. Now there are some concrete operators. So first one is the composition operator. The composition operator C phi is defined by this. C phi of F is equals to F composition phi for F in HD. So there is a historical background of composition operator. So E. Schroeder in 1871 asked the following question. So given phi and analytic cell map of D, point F in HD and lambda belongs to C, say that F of phi of Z is equals to lambda F of Z for F or Z in D. So in the today's language, the equation can be written as this: C phi of F is equal to lambda F, and this amount to inquire about eigenvalues and the eigenvectors of C phi. So composition operators were studied by B. O. Pullman in 1931 in the study of mathematical physics. So in ergodic theory and the diadigmatic system, they are adjoined of parallel Frobenius operator. Systematic study of composition operators on holomorphic function spaces began in 1960 with the work of Norgel, Jerif, and H.J. Schwartz. So next one is the multiplication operator. For xi in HD, the multiplication operator mxi is defined on HD by mxi of is equal to xi into F for F in HD, and the product of these operators is called the weighted composition operators. So actually, sir, there is some problem in the network, so please sorry. So the product of these two composition operators is called the weighted composition operator. So let X and Y be the two Banach species and CXY be the set of all bounded composition operators with holomorphic symbols acting from X to Y. And in case X is equal to Y, then we simply write CX in place of C of XY. And for more information on composition operators, we refer to the reference number 1 and reference number 2. So firstly, in 1989, Overbergson in reference number 3 studied the isolated points, means the singleton component of CH2 in the topology induced by the operator norm, where CHP is the set of all boundary composition operators from HP to HP, and where HP is the Hardy space consisting of function F in HD with the following norm, where sigma is the normalized area measure on the boundary of D. And after that, J.S. Shapiro in 1990, J.S. Shapiro and C. Sunburn in reference number 4 considered this problem in detail, but they could not provide complete characterization of isolated points, but there is the following problems. So number one, characterize the component of CH2. Number two, which composition operators are isolated in CH2. Third one, which composition differences are compact on CH2. So these problems seem quite hard. For problem number one, George Shapiro and Carl Sandburg in reference number 4 suggested the following conjunction, and this is the conjunction. The set of all composition operators that differ from the given one by compact operator form a component in CH2 with the topology induced by the operator. So thus the aim to understand the topological structure of the space of composition operator have led to the study of difference of two composition operators. So many authors intended to solve this problem of compact difference of composition operators on different holomorphic function spaces, but the first complete characterization of compact difference of composition operator was obtained by Bechdel, Oro, and Zhou for H infinity in reference number 5, where H infinity is defined by this, but their characterization involves pseudo hyperbolic distance. Pseudo hyperbolic distance means arc distance between two points in the geodetics, and pseudo means not original distance. So their characterization involves pseudo hyperbolic distance. And after that, Marhouse in reference number 6 solved the problem of compact difference of composition operator in the Bergman space also, but his characterization also involves pseudo hyperbolic distance between the two composition operator. And after that, several authors consider compact difference of composition operator on different holomorphic function spaces, but every characterization of difference of composition operators acting between any two holomorphic function spaces obtained through involves pseudo hyperbolic distance. And after that, Ajay K. Sharma and Ramakrishnan in reference number 7 consider difference of composition operators from fractional Cauchy transform to the digital space. So an interesting feature of their characterization is that they are free from pseudo hyperbolic distance between the two composition operators. So boundedness and compactness of the composition operator from fractional Cauchy transform to the Dirichlet space were considered by Cohen Kim in reference number 8. So recall that the space F of fractional Cauchy transform is a collection of functions F in F which admits the representation of this form, where mu varies over all measures in M, and this space is a Banach space with respect to the following norm. So this is the Dirichlet space is the collection of all functions F in HD for which norm of F D is equals to is finite. And the weighty Bergman space is the space of all functions F in HD such that norm of F AP alpha is finite, where TZ is the normalized area measure on D. So let mu be a positive continuous functionality which we call a weight, and this weight mu is called typical if it is ready. So and this mu mod of Z decreasingly converges to 0 as mod of Z tends to 1. And throughout this paper by weight we shall mean a typical weight. And the weighted block type space B mu on D is a Banach space of all inactive functions F on D such that supremum of Z in D mu of Z mod of F dash Z is finite. And this space is a Banach space with the following norm. And for more about these spaces, we refer to the reference number 9 and 10. So this is the first result, that phi and psi be the two holomorphic cell map of D. Then the difference of two compositional operator from fractional Cauchy transform to the Dirichlet space is bounded if and only if this family is a non-bounded subset of A2, and moreover the following relation also hold. So this is the second result, that phi and psi be the two holomorphic cells of map of D such that C phi from F to D and C psi from F to D are bounded. Then the following statements are equal. Number one, the difference of two composition operator from fractional Cauchy transform to the Dirichlet space is compact. And number two, this integral is the continuous function of X in T. Third one, this family of measures is absolutely continuous. And number four statement is equals to 0. So recently, Zhou and Young in reference number 11 characterized boundedness and compactness of the difference of two composition operator from weighted Bergman spaces to block space, and motivated by these results in this paper, we compute essential norm of difference of two composition operators from weighted Bergman spaces to block type spaces on the unit. And throughout this paper, constants are denoted by C. Main results. Given branch space is X and Y, we recall that the insertion norm of bounded linear map T from X to defined by this. That is the insertion norm of operator T from X to Y is the distance of T from the set of all compact operators from X to Y. And for zeta in D, let zeta be the conformal automorphism D that interchanges even zeta, and n zeta also is defined by this. And the pseudo hyperbolic distance between the two points is defined by this. And for mu, a typical weight and phi xi in SD, let d phi mu and d phi mu are two functions defined by this. So this is the last result of my paper. Let alpha belongs to the open interval 1 to infinity, here p belongs to the open interval 0 to infinity, phi and xi belongs to SD, so the norm of phi at infinity is equal to norm of xi at infinity is equals to 1, and let mu be a weight function so that C phi C xi from AP alpha to B mu is bounded, then the norm of difference of two composition is asymptotically equivalent to this. So these are the references I have used in the paper.
Thank you, sir, for your nice presentation. It was just much appreciated. And now,
Okay,
if there's
sir,
question, let us invite our participants to discuss with you.
Okay, sir.
There is a question, participant. Please ask him, or just drop the message or text in the chat box. If there is no question, just let's go to the next presenter, Dr. Anbala Silva, Research Scholar, Department of Mathematics, University of Aveiro, Portugal. His paper entitled with The Fixed Point Theory Applied to the Study of Fractional Boundary Value Problems. Now, the dear presenter, you are invited to present your work.
Hello, I think that you are seeing my presentation. Yes?
Yes, ma'am, is visible.
Okay, so thank you for the opportunity to present in this conference.
Thank you, ma'am.
So the work that I will present is a joint work with Professor Luís Castro, also from University of Aveiro, Portugal. Our idea in our work is to study 2 points of two specific topics: fractional calculus and the stability. So the behavior of many systems can be described by using fractional calculus, in particular with fractional derivatives like Caputo or Riemann-Liouville fractional derivatives. And the main difficulty in some of these problems is precisely to reach the exact solution. And because of that, the Euler-Mir-Rassia stability is an important tool because we can obtain an approximation of the solution, and we do not need to obtain the exact solution. This is the idea of the use of these Euler-Mirs and Euler-Mir-Rassia stability. The main technique that we use in this work is the fixed point theory, namely the Banach contraction principle. So I will present you some definitions, the problem that we study, and the existence of the solution that is known. Then I will present you the Banach contraction principle, that is the main tool in this work. And I finished showing the uniqueness and the Euler-Mir-Rassia's stability for this problem. So the derivative that we use, the integral that we use in this work is the Riemann-Liouville fractional integral of order alpha, positive order, which is defined by this way, where gamma is the usual, this gamma in here is the usual Euler gamma function. The integral is over 0t, multiplied by this t minus s elevated to alpha minus 1 times this function u, and the Caputo fractional derivative, that is the derivative that we use in this work, is defined by this way. Again, the gamma function n is the integer greater or equal than alpha. In this case, is greater than alpha. Here we have the integral between 0 t, the usual derivative of order n of the function u, and over t minus s elevated to alpha minus n. This n that appears in here, alpha is the order of the integration. Of course, when alpha is equal, alpha is an integer number, we have the usual derivative. So the problem that we study is inspired in this work of 2011, these positive solutions for fractional 4-point boundary value problems, which is defined in this way. We consider additionally a parameter in here. So compared with this work, we consider a parameter in here, which is at lambda that appears in this expression. So in here, we use the Caputo fractional derivative of order alpha. The order alpha that we consider in particular in this work is between 1 and 2. The elements that appear in here, this C and eta, are between 0 and 1. The beta and gamma are between also 0 and gamma, so beta and gamma that appears in the initial conditions. Lambda we consider to be a positive parameter, and the function that we abbreviate by fxt, so is a function of two variables t and x, is continuous and non-decreasing for each t between 0 and 1. The interval that we consider is the interval t in 0 and 1, between 0 and 1. We have also to impose a condition, which is the delta is defined by this relation between the constants beta, gamma, eta, and xi. So when we have these conditions less than alpha minus 1 times 1 minus beta xi, we can obtain the solution. So this is important to obtain the form of the solution, and because of that we will consider these conditions along all the work. So about the solution of the boundary value problem is given by that. So we have in here the delta that I showed you before. The i's that appear in here are the integral, the Riemann-Liouville integral. And we can do a technique that we made we make in the fractional calculus, which is use the green function. So we can rewrite this solution in the form of this integral expression, lambda times the integral between 0 and 1 times the green function. The green function is defined in this way, times the function fx that appears in here. Of course, we will not see this in detail, but we use the theorems that we know for this function g. So, in particular, this green function, we know that when this relation is satisfied, as I said before, we will consider always this relation. The green function satisfies this condition. It is a continuous function. It is between 0 and m times 1 minus s elevated to alpha minus 2. And this constant m is defined by this way. So we will use this result in what follows. As about the Banach contraction principle that we use in this work, we consider this fundamental tool in this work. We consider a generalized metric space and consider a mapping T with a strictly contractive operator. This means that we can call it, so this is a metric, but I will call it a distance. So the distance between the image of x and y by the operator T is less or equal than a constant L times the distance between x and y, where this L is between 0, it could be 0, and less than 1. If this happens, we say that the operator is strictly contractive. And in this case, we have some properties. One of them, which is one of the most important to our work, is that one, the mapping T as a unique fixed point. And we also have the following inequalities. And in particular, in this work, we use the third one. So this property in here, the distance between x and the fixed point is less or equal than 1 over 1 minus L, the L that appears in here, times the distance between x and tx. To use this Banach contraction principle, you use the Banach space of all continuous functions from the interval 0, 1 to R, and we use this finite norm. When we consider this space, of course, we are considering a Banach space. So we are we can apply the Banach contraction principle. When we talk about Euler-Mir stability, we are saying referring this notion. A problem is Euler-Mir stable if there is a constant k greater than 0, such that for each epsilon greater than 0 and each solution of this inequality, this is an inequality, this is not the problem, so this is less or equal than epsilon, the initial conditions are the same, then there exists an exact solution of the problem, and the distance between this y function and the exact solution of the problem is less or equal than k epsilon. To study that, we recall the constant m, which is used to measure the green function. We consider again this condition, and we obtain the theorem. If f is a continuous and non-decreasing function, which satisfies this Lipschitz condition, where L is greater than 0, if the function f has a supremum, that we call that this supremum, we called it n, then the fractional boundary value problem is Euler-Mir stable, provided that L is less than alpha minus 1. The L that appears in here should be less than alpha minus 1 over lambda m, the m that appears in here. To do that, we convert this problem. This is the solution that we know. We convert this problem into a fixed point problem. We consider the operator t defined by this way, and we transform this in a fixed point problem like that. The eventual solutions of the problem will be the fixed points of the operator t. So in this point, we can apply the Banach contraction principle and show that t is a unique fixed point. To do that, we first show that T maps C 0, 1 into R plus into itself. We consider a ball, we consider the supremum, the hypothesis of the lemma, the theorem. We choose an R greater than or equal than this constant. We consider this ball, and we prove that when we compute the norm of this Tx, we can prove using the majority that we know for the function g and function f, we can obtain that this is less or equal than r, which means that t br is contained in this br. So by the continuity of function f and function g, we can say that t is also so it maps this space, this C01 of R plus, so the continuous functions from 01 into R plus, it maps this space into itself. The last point is to show that t is strictly contractive and to prove that we compute the distance between ty and tx. We use the supremum of this function g. We use the Lipschitz conditions from the function f. We obtain that, and so we obtain this inequality. And since we are assuming that this is less than 1, the operator t is a contraction, so we can guarantee that we have a unique fixed point, which will be the unique solution of the problem. Now, to prove the Euler-Mir stability, we consider a function y in this space, which satisfies the initial conditions and also this inequality. And if a function y satisfies this inequality, we can say that there exists a function g which is less or equal than epsilon, and this function g will be equal to this expression in here. So using these 2 points, and of course the initial conditions, we can say that we have a unique solution, x is a unique solution of the problem. And if y satisfies this inequality, then we can rewrite this in this way, and we can say that y is equal to the difference between these two integrals. And using that, we can calculate the distance between x and y. And doing that, We of course use some inequality properties of the modulus,
Hello,
and
ma'am.
also use
Excuse me, ma'am. Please conclude your work within 2 minutes. Time is there.
Okay. So we use again the Lipschitz condition, the majority for the function g, and we obtain this relation to go over this problem. This distance, the distance between x and y are here. Again, we use the so-called Grunwald's lemma, which permits us to go over this problem in here, and applying this Grunwald's lemma, we obtain that the difference between x and y is less or equal than this expression, and we conclude that the fractional boundary value problem is Euler-Meyer stable. Only to say that, since I have no time, only to say that we also prove the Euler-Meyer-Rassier stability, which is very similar, but in this case, in the Euler-Meyer-Rassiers, we use a function phi in here, in this inequality, and also the function phi in this, the distance between x and y. And the techniques that we use are very similar, but in this case, we obtain the same conditions to the problem. So under the same conditions, we guarantee that we have the Euler-Meyer-Rassier stability. We use similar techniques. The only difference in here is that we use another point of the Banach's fixed point theory. Namely, we calculate the distance between y and ty. We measure this distance, and we conclude that the difference between y and ty is less or equal than this expression. Use Banach contraction principle, and we can apply this and obtain the Euler-Meyer-Rassier stability. So this is some of the references that we use in this work, some of the most important references. So thank you very much for your attention. So I finished.
Thank you, ma'am, for a presentation and a great work. Are there any questions from the participant? Question or any query that you have, dear participants? Again, thank you, ma'am, for your work and interesting presentation. Thank you. Now let us go to the next presenter, Miss Shivani, Research Scholar, Department of Mathematics, Kamun University, Almora, India, on her paper entitled on a type of semi-symmetric metric connection in HSU unified structure manifold. Please come, ma'am.
Good morning to all of you.
Good morning, ma'am. Please share your screen.
Yes, ma'am. Yes, sir. I'm sharing. Yeah, am I visible?
Yes, ma'am.
Am I visible, sir?
Yeah, ma'am.
Yeah. So today I'm presenting my research paper, the title on a type of semi-symmetric non-metric connection in HSE unified structure manifold. Myself Shivani Sundrayal, I am a research scholar in SSJ campus Almora, Kumar University, Nainital, under the guidance of Professor Jaya Upreti. So the abstract of my paper is, in this paper, I have studied some properties of semi-symmetric non-metric connection in HSE unified structure manifold and HSE Scalar manifold. Some new results we have obtained in this paper. So first, what is the manifold? Manifold is a topological T2 space. It is a T2 space which is locally Euclidean for every point in M. So this is the general manifold, and then the conditions are added then these manifolds become some particular manifold. So HSU manifold is the specific manifold which I have been used in this paper. So the connection I have used in this paper is a semi-symmetric non-metric connection, which was introduced by SK Chaube sir. And the first these type of connection first introduced by the Haydn in 1932. A linear connection, because a linear connection or Leavitt-Civita connection del is said to be a metric on a manifold Mn if its differentiable value or del G is equals to 0. Otherwise, it is non-metric. And Yano also introduced semi-symmetric metric connection on Riemannian manifold. After that, many geometers like Smrda, Akashik, Shafil, Sen-Gupta, and many other geometers studied various properties and important properties of semi-symmetric metric and non-metric connections on several differentiable manifold, and also defined some new type of connections on Riemannian manifolds. The HSU unified structure manifold is the manifold which have been used in this paper. And this is any even dimensional differentiable manifold of class C infinity is said to be HSU unified structure manifold if it has a structure phi g eta zeta which satisfy the condition 1 and 2. The first condition is phi square x equals to a to the power rx, and second is metric condition is g of x bar y bar is equals to x r a to the power r g of x5, where x bar is a phi x and r can be any number between 0 to n, a be any real or complex number. So then when the equation 1 and the structure of 1 and 2 are satisfied, then Mn is said to be a HSU unified structure manifold. The next one is the connection which I have been used in this paper is semi-symmetric non-metric connection. This connection is a generalized connection which was introduced by Dr. SK Chaube sir in 2019 in his paper Riemannian manifold admitting a new type of semi-symmetric non-metric connection. So this connection is defined by equation number 8 and equation number 9. So this is the connection. Let any what he defined was let Mn be any Riemannian manifold of dimension n endowed with a Levi-Civita connection del corresponding to a Riemannian metric G. A linear connection del tilde delta on Mn G is defined by this equation is said to be semi-symmetric connection. Because it is semi-symmetric connection, so it will satisfy the equation number 9 by the definition of semi-symmetric connection. And the metric of this connection is defined by equation number 11. It also satisfies equation number 10. This connection also satisfies equation number 10, which is where eta is one form associated with the vector field zeta and satisfy this equation. This is given by eta x is equals to g of x xi. This is the value. So now we come to the main results of my research paper. So in this section, we have obtained some results on HSU unified structure manifold and HSU Scalar manifold equipped with a semi-symmetric non-metric connection. So connection I have been used is a semi-symmetric non-metric connection, which was defined by SK Chaube sir. So the first result is in the form of theorem number 1. This is let Mng be a HSU unified structure manifold, then there exists a unique linear semi-symmetric non-metric connection del bar on Mn given by equation number 8 and equation number 9 and equation number 11 and satisfy equation number 11. So these are the equations which I have defined here, 8, 9 and 11. So the proof of this theorem is for the proof of this theorem, we will consider this connection which we have used del bar equals to the in terms of Levi-Civita connection plus a 1-2 type tensor field uxy. So here we have find the value of uxy which is described in this. And finally, we find the value of uxy. This is the value of uxy, and this is the same as defined by Dr. SK Chaube sir. So our connection is compatible for this manifold. So in this theorem, we have find this. In the next theorem, we have we have find some results for torsion tensor on n-dimensional, to n-dimensional, that means it is an even dimensional manifold. So HSU unified structure manifold endowed with this semi-symmetric non-metric connection. So these are some results. These are some relation which we have proved in the next slides. You can see the proof here. These all are some results for the torsion tensor for this connection and this manifold. In the next result, we have defined some relation between semi-symmetric non-metric connection, which is defined by Scalar, and the connection Levi-Civita connection. These two results we find in this theorem. So here the MNG is a HSU unified structure manifold into semi-symmetric non-metric connection del bar and satisfy these relations. In this proof, there are some basic equations we have used there and properties of HSU unified structure manifold and properties of semi-symmetric non-metric connection. So we get we have proved these relations in this theorem. In the next theorem, we have find a relation between hygienious tensor of Levi-Civita connection and the semi-symmetric non-metric connection. So they coincide in the conclusion of this theorem. These two hygienious tensor for these two connections will coincide. So the theorem is like HSU unified structure manifold admits a semi-symmetric non-metric connection. Then the hygienious tensor of Levi-Civita connection and this semi-symmetric non-metric connection will coincide. The proof of this theorem is given by this. Here, an hygienious tensor for our manifold is denoted by tilde n, and the hygienious tensor for Levi-Civita connection is defined by nxy. So here is the proof of this theorem.
Hello, ma'am.
Yes.
Please conclude your work within 2 minutes. Excuse.
Okay, sir. Yeah, yes, sir. Okay, I will. So this is here we have shown that both hygienious tensors will coincide. In the next theorem, in this theorem, we have defined HSU Scalar manifold equipped with a semi-symmetric non-metric connection. And what is HSU Scalar manifold? It is a unified structure manifold is said to be a Scalar manifold if it satisfies this equation. Del x phi of y, if this value is 0, then HSU unified structure manifold is said to be a Scalar manifold. So in this theorem, HSU unified structure, HSU Scalar manifold equipped with this connection satisfy these two conditions. This is again the condition between the connection defined semi-symmetric non-metric connection and the eta values of the manifold. The proof of this theorem is this. The next theorem, in the next theorem, we have defined that the DF, the two form for this, the differential value of this is 0. In this, the F is the two form of HSU Scalar manifold with respect to the semi-symmetric non-metric connection. And the proof of this theorem is given by in these slides. In the last result of this paper, we have find hygienious tensor with respect to the semi-symmetric connection and Levi-Civita connection. Here in this theorem, the hygienious tensor of this connection with respect to the HSU Scalar manifold vanishes. So this is the proof of this theorem, and in the end, the hygienious tensor is completely vanished for this manifold. So these are some references I have been used for my paper. Thank you so much.
Thank you, ma'am, for your presentation, and I appreciate for your work as well, your presentation. Kindly, I requested to the participant if there's question, welcome. If not, let us continue the next presenter. Pushpa Taliha.
Thank you so much. Thank you so much, sir.
Thank you,
Yeah,
ma'am.
I'm stop sharing. Yeah.
Okay. The next presenter, the Pushpalathia Mahalank, research scholar, Department of Mathematics, College of Engineering and Technology, Darhart. His presentation third, the Darkup index of graphs with added edges. Please present your work as much as possible. You have to finish within 10 minutes.
A very good morning and good afternoon to everyone.
Good afternoon, ma'am.
Today I'm going to present my research paper titled Third Zagreb Index of Graphs with Added Edges. Myself, Pushpalta Mahalank. I am from SDM College of Engineering and Technology, Dharwad, Karnataka, India. So this is the collaborative research work with Professor Dr. Ismail Nasi Kangul and Professor Dr. Musa Demirci, Bursa Uldag University, Turkey. So these are the contents of my presentation. So this is the abstract of my paper. So in this paper, in the graph theory, we have edge division and edge addition are the most important combinatorial methods. So which enables one to calculate some properties of a graph by means of similar and usually simpler graphs. In this paper, we are considering the change in the third Zagreb index of a simpler graph G when an arbitrary edge is added. The effect of adding any kind of edge to a graph is shown to be an integer congruent to modulo 2, modulo 6. This result can be used to calculate the third Zagreb index of larger graphs in terms of the Zagreb indices of smaller graphs. So in this paper, we have calculated the change of Zagreb indices of path graph, cycle graph, star graph, complete bipartite graph, and also tadpole graphs. So this is the introduction. In this paper, throughout this paper, we are considering the simple graphs G with the vertex set V and edge set E. So here we are denoting the degree of the vertex V by dg of V. Here we are considering the pendant vertex. Pendant vertex means the vertex with degree 1 is called a pendant vertex. Similarly, edge consisting of a pendant vertex is known as pendant edge. So here we are denoting the path graph by Pn, cycle graph by Cn, star graph by Sn, complete graph by Kn, complete bipartite graph by KRS, and tadpole graph by TRS. So here we are considering the simple graph G. Simple means it should not be having any loops or multiple edges. So here in this paper, we are calculating the change of the third Zagreb index when a new edge is added to a given graph G. The new graph after adding the edge E will be denoted by G plus E, and the original graph is denoted by only G. And here we are considering both the graphs G and G plus E as simple graphs. So here we have used some definitions. So these are the definitions of first and second Zagreb indices. Directly, I'll go to the third Zagreb index because in this paper we are using the definition of third Zagreb index. That is denoted as MT of G, that is also equal to F of G. Sometimes this third Zagreb index is known as forgotten index, that is equal to sum of dVq, where V belongs to the vertex set V. So here, third Zagreb index means it is the cube of the vertex degree. Sum of the cube of the vertex. So here we have one theorem, adding a new edge to a graph. So in this section, we are considering a simple graph G. Here we have two cases. In the first case, we are adding a pendant edge, and in the second case, we are adding a non-pendant edge. Already I have told you pendant edge means the vertex with degree 1, and non-pendant edge means it is not a pendant edge. So here in the first case, we are adding a pendant edge to a graph G. For that, we are considering the Zagreb index. So here we calculated the change in the Zagreb index of G plus E, that is equal to third Zagreb index plus 3 into di plus 1 minus 1. Similarly, we have the second result when we add the non-pendant edge, that is equal to the Zagreb index plus 3 into di plus 1 plus dj plus 1 minus 1. So using this theorem, we have calculated some of the results using path, cycle, star, complete, complete bipartite, and tadpole graphs. We consider the two results. First one is adding a pendant edge. Second one using the case by adding non-pendant edge. So first we consider the path graph. Due to shortage of time, I'll not explain all the results. Just I'll show you the results. So here we have calculated the third diagram index for path graph, that is empty of Pn equal to 8n minus 4. So using the theorem, we have calculated when the results, when pendant edge is added and when that edge joins the two existing vertices Vi and Vj. So based on that, we have different possibilities for the path graph Pn. So when a pendant edge E is added to one of the endpoints, then this is the result, that third diagram index of path graph plus E is equal to 8n minus 6. Similarly, it is when it is added to one of the midpoints of Pn with degree 2, that results is equal to 8n plus 6. Similarly, a non-pendant edge is added to two vertices Vi, Vj, so that Di, Dj equal to 1. Then the diagram index value is 8n. If we consider Di equal to 1 and Dj equal to 1, means the degree, first degree is 1, second degree is 2, or vice versa, then the value is equal to 8n plus 2, 8n plus 12. Finally, if Di equal to Dj equal to 2, both the degrees are equal to 2, then we have the result 8n plus 24. So based on these results, we have concluded here, this is the corollary, when a new edge is added to a path graph, either it may be a pendant edge or a non-pendant edge, the third diagram index increases by either 8 or 14 or 20 or 26 or by 38. So this is about the path graph. Similarly, we have the results for cycle graphs. So third diagram index of cycle graph is 8n. Again, using the same theorem, when we are adding the pendant edge, this is the result. And when we are considering the non-pendant edge, which joins two existing vertices Vi, Vj, this is the result. So based on these, we have different possibilities for the cycle graph Cn. The first case is when the pendant edge is added to any of the vertices of degree 2, the value is equal to 8n plus 20. If a non-pendant edge is added to the vertices Vi, Vj, the value is equal to 8n plus 38. So based on this, we have wrote one corollary here. When a new edge is added to a cycle graph, either it may be a pendant edge or a non-pendant edge, its third diagram index increases by either 20 or by 38. Similarly, we have the results for star graph Sn. Star graph means the value of n should be greater than or equal to 3. So the diagram index for star graph is n minus 1 plus n minus 1 whole cube. So using the theorem, again we have two different results for pendant edge. When we are adding the pendant edge, this is the result, and when we are adding the non-pendant edge, this is the result. Based on this, we wrote some possibilities. So when a pendant edge is added to vertex Vi of the star graph Sn having the degree 1, so the value of that is equal to n plus 7 plus n minus 1 whole cube. When a pendant edge E is added to the vertex Vi of Sn of degree n minus 1, then the value is equal to n plus n cube. If we are adding a non-pendant edge to the vertices Vi, Vj, both are having the degree 1, then the value is equal to n plus 13 plus n minus 1 whole cube. If a non-pendant edge is added to the vertices Vi, Vj of degrees 1 and n minus 1, then the value is equal to 8 plus n cube. So using these, we wrote one corollary here. When a new edge is added to the star graph Sn, its third diagram index increases by either 8, 14, 3n square minus 3n plus 2, or by 3n square minus 3n plus 8. It may be a pendant edge or a non-pendant edge. Similarly, we have the similar results for complete graphs Kn. So these are the results. Just I'll skip these. Similar results we have here. So using these, we wrote one corollary here. When a new edge is added to a complete graph N, its third diagram index increases by either 2n cube plus 3n square minus 3n plus 2, or by 6n square minus 6n plus 2. Similarly, we have the same results for complete bipartite graph KRS. So third diagram index of KRS, that is complete bipartite graph, is RS into R square plus S square. So using the theorem, we have two different results. First one is for whenever we are when we are adding a pendant edge. Second one is for when we add the non-pendant edge using two existing vertices Vi, Vj. So here we have different possibilities. So the corollary is when a new edge is added to a complete bipartite graph KRS, its third Zagreb index increases by either 3r square plus 3r plus 2, or by 3s square plus 3s plus 2, or by 6r square plus 6r plus 2, or by 6s square plus 6s plus 2, or by 3 into r square plus s square plus r plus s plus 2. So now we have the summary and conclusion. In this paper, the effect of edge addition to any connected simple graph on its third Zagreb index is studied. So this will be very useful when we are considering the larger graphs. Directly we can't calculate any calculations using the larger graphs. So we have used here simple graphs. So this differs for adding a pendant edge or a non-pendant edge. Both effects are formalized in this paper. And this is calculated for 6 most frequently used graph classes like path graph, cycle graph, star graph, complete bipartite, and tadpole graphs. And there will be a continuation of this paper for other indices. So these are the references.
Thank you, ma'am, for your appreciated work and interesting presentation. Actually, you have covered within 10 minutes as you have discussed. So just let's me invite some question if there is for the participant. Let's give me a chance for that.
Yes.
There any question from the participant? Please let me know. Thank you, ma'am. Again, so much.
Thank you, sir. Thank you for all the organizers for giving me an opportunity to present my paper in this conference. Thank you.
Thank you, ma'am. The next presenter, Mr. Suleiman Timothy, Assistant Lecturer, Department of Primary Education, Federal College of Education, Nigeria, for his presentation, one-step 5-point hybrid block method for the solution of initial value problem for third-order differential equation. So please come with us, dear presenter. Hello, Mr. Suleiman. Hello. Hello, Mr. Suleiman from Nigeria. You have a chance to present your work. Let me give you a chance. Okay, the next presenter, Mr. Wudinet Lahun, lecturer, Department of Mathematics, Debre Tabor University, Ethiopia. He's entitled with cryptographic scheme of Laplace transform in Amharic language. So you have to use 10 minutes for presentation and 5 minutes for discussion. Hello, Mr. Abdullah. Am I audible? Go to next. Okay, the next presenter is Swanpa, research scholar, Department of Mathematics, the Center of Higher Education.
Hi,
Are you
sir.
present, ma'am?
Yes.
Yeah, please continue your work. We are
Okay.
waiting, ma'am. Okay, ma'am. You have 10 minutes for a presentation, 5 minutes for discussion. You have to cover within such time, huh?
Okay. Sir,
Okay,
am
ma'am.
I audible?
Yeah, you are audible.
Visible?
Yes,
Okay.
visible, ma'am.
Good afternoon. I'm Swapna Ravinder from Nonlinear Center for Higher Education, Kanyakumari. My business topic is some combination to cordial labeling of ladder graphs. Before coming to the topic, I am talking about graph labeling. Graph labeling is an assignment of integers into vertex set, edge set, or both under some conditions. So I am defining a new kind of labeling, some combination to cordial labeling inspired from two labeling techniques. Before coming to the topic, I am just introducing the combination labeling, the inspired work to you. The combination labeling is also an assignment of integers to the vertex set with it's a bijective mapping from the vertex set to the number of vertices. That is, a graph consists of vertex set and the edge set. Here we are representing with P the vertex set. So the mapping psi from vertex set to 1 to etc. P is the set of vertex. Then there exists a function psi of L C psi of M. If psi of M is greater than psi of L, and also psi of L is greater than psi of M, if psi of M is psi of L is greater than psi of M. This is it the psi of L C psi of M is the total number of combinations of psi of L things taken psi of M at a time. This is actually combination. So this kind of labeling is called the combination labeling. This can be represented by a figure from the figure. In this figure, this is a simple graph. In this, we can see for each vertex, the vertex at 1, 2. You can see that this particular graph consists of 7 vertices. So for each vertex, we labeled with 1, 2 up to 7. In the way psi of L, before we discussed psi of L, C psi of M. In that way, we are represented at the whole graph. Here for each vertices 1, 2. 2 is greater than 2, so 2C, 2, that 2 is represented to the edge. That is the induced function that is represented to the edge. And again 4C2, 6, and the next one, I'm not visible. When the lower part 3, 5, that is 5C3, 5C3 is 10. Then 4C3, 4. In that way, we represent the whole graph. In this, no two edges repeat the same labels. This kind of labeling is called the combination labeling. And again, another kind of labeling. This labeling was introduced by Pondraj et al. In 2015. This is also a one-to-one function, but from vertex set to the 1 to etc. P. P is the vertex set. Here, the induced function we have taken is LCM or MCL. According as L is greater than M, which L is less than, which one is greater? That is we have taken. In this labeling, this is actually combination cordial labeling. Cordial labeling, we have taken the cardinality of the number of labels represented with even numbers. We are representing as 0, and odd numbers we are represented as 1. So cardinality of E psi of 0 minus E psi of 1 is less than or equal to 1. That is the condition. Both these condition holds, then the graph is called parity combination cordial graph, and this kind of labeling is called the parity combination cordial labeling. And this is a figure of a star graph K1 4. In this, we are represented the central vertex with 1 and the pendant vertices with 2, 3, 4, 5. For the better understanding, I tell you that 2 is greater and 1 is less. That is 2C1. That is 2. This is an even number. So we are representing for the even number as 0. So the edge label becomes 0. And 3C1 is 3. So we are represented, it's an odd number. So it's a 1. In this method, we represent the whole graph. So the number of vertices labeled, number of edges labeled with 1 and 0. That is 2 minus 2, which is less than or equal to 1. This is the labeling technique. So inspired from this, I define a new labeling, sum combination to cordial labeling. In this, we have taken the sum of two functions, two vertices. That we have taken the induced function and also the condition of a cordial labeling, cardinality of E psi of 0 minus E psi of 1, which is less than or equal to 1. this condition also holds for the graph. Then that kind of graph is called a some combination to cordial graph, and the labeling is called the some combination to cordial labeling. In this paper, we are contributing some ladder graphs that holds the particular kind of labeling. Okay. There is the first here, and this is the figure of a slanting ladder. This is the figure of slanting ladder. In this slanting ladder, represent upper vertices we can represent as Vi. The lower represent part we can represent as Ui. We represent the first part of vertices with 1, 2, 3 up to the number of vertices 8. So for each pair of vertices, when we are calculating the LCM, L plus M P2, we obtain the graph as holds E cardinality of E psi of 0 minus E psi of 1 is less than or equal to 1. So this kind of graph is holds the slant some combination to cordial labeling for every graph for each n. The next one is also a triangular ladder graph. This is a figure of a triangular ladder graph. In this graph also, we are representing the upper part of the graph vertices with 1, 2, 3, 4, and the lower part with consecutively the lower part. We can see for each vertex. In the previously said methodology we are applying 2C1 is 2 and 5C2. This method we can represent the edge labels also. The number of labels representing E psi of 0 minus E psi of 1 is also less than or equal to 1. This kind of this thing is holds for n greater than or equal to 4. The triangular ladder with the vertex set is greater than 4. The graph holds this property. This is another figure. This is also a ladder related graph. This is open triangular graph. This also the same way we can represent the upper part of the vertex and the lower part of vertex. Also we can represent in this. Hello?
Yes, ma'am, carry on.
Okay. In this way also we can represent the whole graph in this. Hi.
Please, ma'am, carry on.
Okay. We can represent the whole graph. In this also, when we compute the L plus M C2, the whole graph, the cardinality of 0 and 1 is less than or equal to 1 for this graph also. And this one is another ladder related graph is called a closed ladder. The closed ladder consists of internal vertices and the external vertices. We can label the internal vertex and external vertex in the way that I take the external vertex as 1, 2, 3, 4 and the internal vertex with 5, 6, 7, 8. You can take in any form because labeling is not a unique one. You can take in any form, but the condition should hold for that is the main thing. Okay. So for each vertex, for each edge also, E psi of 0 minus E psi of 1 is less than or equal to 1 toward the graph. This is another one. This is a step ladder. Step ladder, we can take on the vertex. We can label the first step of vertex with 1, 2, and the next step of vertex with 3, 4, 5. So consecutively, we can label the n step. So the graph, this graph also holds the property, but when n greater than or equal to 4, this pattern holds. You can try another pattern also for your convenience. This graph also holds the condition, the edge condition also satisfies, and that is a cordial labeling condition that also holds. Okay. Maybe we can find some combination to code. This one different class of graphs or different graphs. These are the few references I taken for preparing this article. Thank you.
Thank you so much, ma'am, for your nice presentation. Any question from audience? I think there is no question. Thanks again, ma'am.
Okay, thank you, sir. Thank you. Thank you for the university also for giving me such a wonderful opportunity. Thank you, sir.
Thank you so much, ma'am.
Thank
Now,
you.
I would like to call Ms. Divya Agrawal, Senior Research Fellow in the Department of Mathematics, Indraprastha Institute of Information Technology, Delhi, India. The topic of our presentation is splitting subspaces of linear operators over finite fields. Ma'am, are you available? Ms. Divya
Yes, I'm
Agrawal?
there. Yes,
Okay,
I'm
ma'am.
there. Thank you for giving me the opportunity to speak in the conference. We'll talk about splitting subspaces of linear operators over finite fields. This is an enumerative combinatorics talk. Please feel free to stop me anywhere you have questions, comments, or suggestions. Let me just go full screen. So we'll begin with defining splitting subspaces, and then we'll see the connection of splitting subspaces with Krylov subspaces. Now to discuss results about splitting subspaces, we will see what is similarity class type of an operator. Then we will see what is the number of splitting subspaces for cyclic nilpotent operators. And finally, we will discuss future directions for research. So suppose V is an MD dimensional vector space over the finite field FQ, where Q is a prime power and M and D are positive integers. And P is a linear operator on V. Now a subspace W of V of dimension M is said to be T-splitting if we can write V as this direct sum. W, direct sum TW, T square W up to T to the D minus 1 W. So note that each of these subspaces have dimension M here. And so in total, the dimension of the right hand side equals the dimension of the left hand side, which is MD. And denote by sigma MDT the number of m-dimensional splitting subspaces for the linear operator T. This definition is motivated by the work of Niederreiter on pseudo-random number generation in cryptography. And determination of sigma MDT for an arbitrary operator T is an open problem. Now let us first discuss the connection of splitting subspaces with Krylov subspaces. So again, let T be a linear operator on an n-dimensional vector space V over the finite field FQ. And suppose V1, V2, Vm is a set of m vectors in V. The Krylov subspace of order D generated by S is defined this way, where degree of Fi is less than D for each I. In other words, Krylov subspace generated by S is the span of the vectors V1, TV1 up to T to the D minus 1 V1, V2, TV2 up to T to the D minus 1 V2, and so on up to Vm, TVm up to T to the D minus 1 Vm. We may also define kappa MDT, which is equal to the number of ordered tuples V1, V2, Vm such that the Krylov subspace generated by that tuple is all of V, and divide that by the total number of ordered tuples possible in V. So essentially this kappa MDT is the probability of selecting m vectors uniformly and independently from V such that the Krylov subspace generated by those vectors is all of V. Now Krylov subspaces have applications in various areas of mathematics. They also have applications in real life. So if we have a real life problem, we make a mathematical model of the problem, and eventually we get to solve a system of linear equations. Now that system is very large and sparse, consists of large number of variables and very large number of equations. So Krylov-based methods and this kappa MDT prove to be very useful in solving such systems, and those systems arise in number theory and computer algebra. These methods are also useful to determine the minimal polynomial of large matrices over finite fields. And the probability kappa MDT is relevant to the efficiency analysis of such algorithms. and obtaining bounds on kappa MDT is stated as a difficult and important problem. Yes? Okay, so obtaining bounds on kappa MDT is stated as a difficult and important problem in many research papers. For another instance of the relevance of Kulob-based methods, we have number field sieve, which is used to factorize large integers. This also relies on Krylov subspace methods. And we have applications of Krylov methods in quadrature methods, analytic theory of continued fractions, infinite series expansions, orthogonalization algorithms, and the mathematical foundation of quantum mechanics, to name a few. So let's discuss the connection of Krylov subspaces with that of splitting subspaces. So if we have an operator T on an m-dimensional vector space over the finite field FQ, then Krylov subspaces and splitting subspaces are related by this equation. So here gamma QM is the number of ordered bases of an m-dimensional vector space over the finite field FQ. So this quantity is well known. Gamma QM is known. So this is q to the m minus 1 times q to the m minus q up to q to the m minus q to the m minus 1. This is known. So if we know kappa MDT, then sigma is known and vice versa. Now to discuss results about splitting subspaces, let us see what the similarity class of an operator is. So suppose T is a linear operator on a vector space V. Then T defines an FQX module on V where the action of X is that of T. Now, by fundamental theorem of modules over PID, this module can be decomposed as this direct sum, where phi i's are monic irreducible polynomials, and corresponding to each phi I, we have a partition, integer partition lambda I. In fact, these phi i's are the invariant factors of the operator T, and these lambda i's, we can determine these lambda i's using cyclic decomposition theorem, which is a classical result of linear algebra. So these phi i's together with the partition lambda i's form the similarity class for an operator. Note that similar operators have the same similarity class. And so if we consider di to be the degree of phi I, then di lambda I form the similarity class type of an operator. For instance, if the module decomposition for an operator is this, then the monic irreducible polynomial here is x plus 1 and the corresponding partition is 2, 1. So similarity class of T is x plus 1 to 1, and since the degree of x plus 1 is 1, so similarity class type of T is 1 to 1. The notion of similarity class type goes back to the work of Green on irreducible characters of finite general linear groups. One of the reasons for considering similarity class type is because many combinatorial invariants depend only on the degrees of the polynomials and not on the polynomials themselves. So we proved that if we have two similar operators, T and T prime, then the number of splitting subspaces for both the operators coincide. This is an easy result. So because T and T prime are similar, so we have an isomorphism S, such that T prime is equal to S of T of S inverse. Now subspace W is T splitting if and only if SW is T prime splitting. So we have a bijection between the splitting subspaces for T and that for the splitting subspaces for T prime, and therefore these two quantities are equal. But we proved something more than this. We proved that if two operators have the same similarity class type, even then the number of splitting subspaces for both the operators are equal. And with the aid of this result, we may define sigma MD tau, where tau is a similarity class type, to be the number of splitting subspaces for an operator whose type is tau. This quantity is well defined because of our result. The next result that we prove is that for MD and tau fixed, sigma MD tau is a polynomial in Q. For instance, when M and D both are 2 and taus are these, then we can see that sigma 2 tau is a polynomial in Q for each of these taus. We have computed these using Sage math, using codes in Sage math. Now, finally, let's come to cyclic nilpotent operators. So we proved that For cyclic nilpotent operators, the number of splitting subspaces is given by the simple formula q to the m squared into d minus 1. And we may generalize this result to the type 1 MD because of our previous discussed result. So we know that cyclic nilpotent operator have characteristic polynomial x to the MD. So there is only one monic irreducible polynomial, that is x, and degree of that polynomial is 1. So we have a 1 here. And since the operator is cyclic, there is only one part in the integer partition, and that part is MD. So for this type, for any operator of this type will have the number of splitting subspaces equal to q to the m squared into d minus 1. So let's discuss some future directions for research. Now we have proved that sigma md tau is a polynomial in Q. So one may try to prove that no matter what tau we take, this polynomial will have degree m squared into d minus 1. So this degree will remain the same. Also, the problem of determination of sigma mdt for an arbitrary assignment of the operator t remains open. Here are some references of the talk. Thank you so much for attention.
Thank you, ma'am, for your wonderful presentation, as well interesting work. May there is question from the participant? Participants have question or any comments that you have, please discuss with her. I think there is no question, ma'am. So thank you very much again.
Thank
Have
you,
a nice
sir.
day.
Thank you.
Yeah, the next presenter just Mr. Udinet Laun from Dabar University, Department of Mathematics, Ethiopia. So please join with us. We are waiting you.
Am I
for your
audible?
presentation.
Am I
You are
audible?
audible, sir.
Okay.
Please share your screen.
I'm sharing, sir.
Okay, sir.
I continue.
Yeah, really, you have to continue.
Okay, thank you for this chance. My paper title is Cryptographic Scheme of Laplace Transform in Amharic Language. I am going to present, or I am going to induce the Laplace transform in cryptography. Let me present my outlines. I do have introduction, definition and standard results, proposed work, generalization and conclusion. As I told you, my topic is cryptography scheme of Laplace transform in Amharic language. Let me tell you something about Amharic language. Since the 13th century, Amharic has been the official language of the country, or working language of the country. According to the 1994 census, Amharic is the most commonly spoken language in Ethiopia. The language is the working language of the federal government of the country. It's a Semitic language of Afro-Asiatic language groups that related to Hebrew, Arabic, and Syrian. And it's the most spoken language, the second most spoken Semitic language in the world, next to Arabic. As its own from, it takes some letters from, I mean, most of the letters from Giz, and it looks some letters from another language also. And it's a writing style is from left to right. And let me tell you about something about Laplace transform has many applications in various fields. Now I'm going to use this, the application of Laplace transformation in cryptography. Fundamental objective of cryptography is to enable two people to communicate over insecure channel in such a way that an opponent cannot understand what things are discussing or they are talking. So the cryptography will help us to encrypt or decrypt those communications. So encryption is the process of securing information to make unreadable without special knowledge. And the decryption is the vice versa of this. This is usually done for secrecy and typically for confidential communication. And a cipher is an algorithm of performing this encryption or decryption as well as. The original formation is known as plain text, and that one, the decrypt one, is cipher text. A cipher text message contains all the informations the sender sends to the receiver, and the plain text is the original message. Ciphers are usually parameterized by a piece of auxiliary information called case. By changing this case, we are going to send a secure message for the receiver. Now, let me go to the definition and standard results. As you know, the Laplace transform is defined as the integral of e to the power of minus stf of dt for the given function. This is the Laplace transform of the given specific function f of s, provided that the integral exists. Here the parameter s is a real or complex number. So the corresponding inverse Laplace transform also, the Laplace inverse transform of f of s is given by f of t as well. It has its own linearity property. It's given by Laplace of f of t is f of 1s, and Laplace of f of t is f of 2s. Then the Laplace transform of c1 times f of 1t plus c2 f of 2t plus c3 f of c3t and so on is the same as c1 Laplace of f of 1t1 and c2 Laplace of f of 2t and c3 Laplace of f of 3 for any n number of functions. Hence, the Laplace transform is the sum of two or more functions of t is the sum of the Laplace transform of the individual functions. It means that. Now let me go to some standard results that I'm going to use on this paper. I think I'm going to use three of them. Laplace transform of t to the power of n is given by n factorial over s to the power of n plus 1 for n is an element of the set of natural number, and the inverse Laplace transform of n factorial over s n plus 1, which is equals to t to the power of n, and the Laplace transform of cosine of kt, which is equals to s over s square plus k square, and the inverse is also. Finally, the third one is the Laplace transform of t to the power of n times f of t is given by the d by ds of the power of n minus d by ds of the power of n f of s, and the inverse is also given. Now let me go to the Amharic language letter conversion rule. I'm going to use for the following table, each set of the English letter in red color is the keyboard combination required to get the Giz character. For instance, I circled ha to the Amharic letter ha is written as HE. We are going to consider. We can use also another rules as you want. La as LE, Ma as MA, and so on. And so on. Here I have circle also as X and F as F. I'm circling these four letters because I'm going to use as a word that I'm going to send a message for in Amharic language. So the Amharic transcription is, before we are going to encrypt or decrypt the given sent received message, first we must change the Giz alphabet to English transcription as presented up in the above table. Suppose the sender wants to send the message Masih, which meaning for the international community, the Masih means book. And first we are going to use the transcription Ma as MA, C as X, Ha as HA, and E as F. After getting its transcription, we are going to encrypt or decrypt this message. This the red message MAXHAF. So after getting its transcription, we are going to encrypt and decrypt. Now let us going to use the encryption procedure. Let us consider cosine of kt, which is equals to the power series expansion of cos kt is given by 1 minus k square plus t, k square times t square over 2 factorial plus k to the power 4 to the power 4 over 4 factorial, and continue with the same manner and summarized in this manner. So where k is a constant and multiplying by this the above cosine of kt by variable t, we will get t minus k square t cube over 2 factorial and k is constant. Now let us allocate 0 to A and 1 to B, then Z will be 25, starting from 0 for A, 1 to B, C for 2, and so on. Z will be 25. Suppose the sender wants to send the previous message Masih, whose meaning is book, and the English transcription is MEXHEF. So MEXHEF is equivalent to 12, 14, 12, 4, 23, 7, 4, 5 means M is 12, E is 4, X is 23, H is 7, E is 4, F is 5. So we are going to denote this, G0 which is equals to 12, G1 which is equals to 4, G2 which is equals to 23, and so on. Now we are going to multiply the given function f of t by g, and g of f of t is given by g t cos to t, taking that k which is equals to 2. The constant k is 2, cos to t is derived from it. So taking the common t times g0 times the first power series expansion of cos 2t, 1, which is g0 times 1, g1 times the second power series expansion of cos 2t, which is 2 square plus t square, and so on. Finally, we'll get 12t minus 4 times this one. Then taking the Laplace transform of this type of equation, 12t minus 4 times 2 to the power of 2t cube over 2 factorial and so on, by Laplace transform of this will be 12 over s square minus 4 times. Finally, we'll get 12 over s square, 48 over s4, 1840 over s6, and so on. And so on. Then we are going to take these numbers, 12, 48, 1840, 31, 36, 92, 16, and taking the quotient of this, we will get 12 is written as 26 times 0 plus 12. So we will have remainder 12. Or we can write as 12 congruent to 12 modulo 6, 26, 48. Similarly, 26 times 1 plus 22, 1840 as 26 times 70 plus 20. So 20 will be our remainder. So taking these remainders, let hi which equals to ri, which means the remainder of the previous result. So h0 will be 12, the first remainder here, and the second remainder will be 22, the third remainder will be 20, the fourth will be 16. So h0 will be 12, h1 will be 22, h2 will be 20, h3 will be 16, and so on. With case 0, 1, 70, which are the factors. Hence, the message MEXHF, which is must have, gets converted to MWUQMA, because M stands for 12, 22 stands for W, 20 stands for U. From the previous assumption, A for 0, B for 1, and so on. Now we are going to transcribe to the Amharic language this MWUQMA by the above table. Will get MEWMA, which the receiver will see this message. The receiver or the hacker, it might be. So the decryption process will be similar, but we are going to apply, instead of Laplace transform, we are going to apply the inverse Laplace transform of the given function, or the given function, which is t cos to t, it means. So let h0 provided before 12, h1 22, and h2 20 as well, using given ki, previously the factors 0, 1, 70, 120, and so on. Now the inverse Laplace transform of this given function will be given by this the last equation, 12t minus 4 times to the power of 2 t squared, the previous original equation. So taking these coefficients 12, 4, 23, 7, 4, and 5, we are going to use by the given table, we are going to get again Masih or MAXHEF, it means. So the generalization for this work is for encryption of given message in terms of GI, we consider f of t equals to gt equals to t for artisan element of natural number, where n is the set of natural numbers, taking the Laplace transform, and we follow the procedure discussed in the proposed work section. Then we can convert the given message GI to HI, and as well HI to GI, where HI is given by in this manner, HI which equals to GI times Ri times I plus 1. And we can conclude taking inverse Laplace transform and using the procedure discussed in the proposal section, we can convert given received message HI to GI also by this formula, GI which equals to 26K plus HI over Ri times I plus 1. The illustrative example for this work is using the results obtained in this paper. If we have original message Masih, then it gets converted to MG with Ki for I which equals to given numbers, or R which equals to 3, means that for the function cos 3t, for the function cos 3t, or t times cos 3t. The second one, Mickey O for R which equals to 4, means that for cos 4t, and similarly for R which equals to 5 and R which equals to 6, we can get different results. So my conclusion for this study is a new cryptographic scheme is introduced in Amharic language using Laplace transform, and the private key is the number of multiples of mod n. The results in this section provide us many transforms as per the requirements, which are the most useful factor of the changing the key. As per changing the k which equals to 2, 3, 4, and 5, we will get different results for the receiver. Therefore, it's very difficult for an eyedropper to trace the private key either by the brute force attack or by any other attack. It's more secure than other techniques. So these are some of my references of my work. Thank you very much.
Many thanks, dear presenter. Woodner from Deborah Tabor University, Department of Mathematics. Just I stand with the recognition with your work and presentation as well. If there's some question from the participant. Any question? Okay, thank you, Mr. Woodner.
Thank you very much.
Thank you in advance. The next presenter, just or the last paper that we have to be held, Mr. Mutuku Karabe from the Department of Mathematics, Mizan-Tepi University, Ethiopia, for his paper entitled with the analysis of modified model for transmission dynamics of hepatitis B virus disease. So we have to present your work within 10 minutes and 5 minutes with discussion. You have to use time properly. Welcome, sir.
Okay.
Dear participant, this is the last work, the last presentation for this session. Afternoon time, it will be started by 2 p.m. Eastern Africa time or 7 start.
Okay. I can click the screen.
Yeah, you have to share your screen and you have to start your presentation as much as possible.
Yeah. I click share and then click screen.
I think it's not visible for us. It's better to Mr. Teno, please help you.
እሺ ነው። እሺ አሁንም ሸር Sir. Sir.
Yes, it's not visible.
It asks permission.
Which permission?
Which permission, sir?
Sharing permission, yeah.
Dear Suleiman Timothy from Nigeria, are you ready to present your work? I'll give you a chance for you. Dear Suleiman.
Mr. Suleiman.
Mr. Suleiman, are you available? Mr. Suleiman from Nigeria, are you available, sir? Thanks all the presenters and participants. Now this is the time to present a certificate of appreciation to our today's keynote speaker, Dr. Advin Massey. Now I request Mr. Vandemagan Addis, the Academic Program Director of Mizan-Tepi University, Tepi Campus. Sir, I request you to present a certificate of appreciation to Dr. Advin Massey. I think there is some connection issue. So on behalf of Mr. Vandemagan Addis, I am presenting the certificate of appreciation to Dr. Advin Massey, Assistant Professor in the Department of Mathematics, Manav Rachna University, Faridabad, India, for participating as a keynote speaker in the first international conference on recent researches in mathematics, organized by the Department of Mathematics under the College of Natural and Computational Science, Mizan-Tepi University, Tepi Campus, Ethiopia. Sir, we are very thankful to you. We are also very thankful to all presenters, all participants. Thank you so much. The next session will be started at 2 o'clock by Ethiopian time, and the link is same for the WebEx session. So after lunch, we will meet again. Thank you so much.